Space and time seem so natural that most people never stop to question them. You wake up and find yourself surrounded by space, stretching in every direction. You sense time passing from moment to moment, carrying you from the past toward a future that feels open and undefined. You walk through space as if it is a stable stage, and you move through time as if it flows independently of everything else. These impressions feel obvious because they have guided every moment of your life, yet they hide a truth that is far stranger, far deeper, and far more profound. Space and time are not simple containers in which the universe exists. They are not separate, they are not fixed, they are not passive. Instead, they are woven together into a single, dynamic fabric called space-time. And everything that exists, every particle, every star, every galaxy, every thought, plays out on this evolving, four-dimensional landscape. Understanding space-time means seeing reality from a perspective that ordinary intuition cannot provide, because intuition was shaped in a world where the true nature of reality lies hidden behind gentle approximations. When you look around, the world feels three-dimensional, but this is only half the story. The missing piece is time, which joins space to create a four-dimensional continuum. An event is not defined merely by where it happens, but also by when. A place without a time is meaningless, and a moment without a location is incomplete. Every experience you have ever had exists as a point in space-time, not in space alone. Your entire life is a path, a world line, traced through this fabric. You're not moving through time separately from space. You're continuously moving through space-time, moment by moment. The same is true for every atom in your body, every planet in orbit, every ray of light crossing the universe. The idea seems simple, yet it radically changes what reality is. It means the universe is not unfolding in front of you. You are part of the unfolding. Your existence is written into the geometry of space-time itself. This realization did not come naturally to humanity. For centuries, people believed space was empty and unchanging, a stage that existed independently of the actors. Time was imagined as an absolute flow, the same everywhere and for everyone. These ideas worked well enough to launch ships, build bridges, farmland, and navigate the planet, but they were not the true structure of the universe. They were approximations shaped by life at slow speeds and low energies, in a gravitational field too weak to reveal the deeper nature of space-time. Human intuition evolved to handle simple motions, not the distortions that occur near the speed of light or the curvature that emerges near massive bodies. That is why the truth remained hidden until scientific tools could measure what senses could not. Even though space-time determines every movement you make, you cannot directly feel its curvature. You cannot sense time slowing down or space stretching around a massive object. But these things happen constantly. Time runs a little faster at the top of a mountain than it does at sea level. Time runs slower for someone in orbit than for someone on Earth's surface. If you could see space-time around the sun, you would see it curve gently like a valley, guiding Earth's orbit not through force but through geometry. Light travelling past a star bends, not because something pulls on it, but because it follows the straightest possible path in a warped geometry. These effects are so slight in everyday life that you do not notice them, yet they lie at the heart of the universe's structure. The strangeness becomes even more intense when you consider how time behaves. Time does not flow uniformly. It is not a universal rhythm. It depends on your motion and on the gravitational environment around you. A fast-moving astronaut ages more slowly than someone on Earth. A clock placed in a stronger gravitational field ticks more slowly than one placed in a weaker field. These facts are not science fiction. They are measured realities. Without correcting for relativistic time dilation, GPS systems would become useless within hours. Your phone can only tell you where you are because Einstein understood how space-time works. The everyday world appears simple because human life exists in a narrow band where space-time behaves almost flat. But if you step outside that band, the simplicity evaporates. This raises a profound question. If space and time are not absolute, if they can bend, stretch, warp, and evolve, what is space-time actually made of? It is not a substance in the traditional sense. It is not built from atoms or particles. Instead, it is a geometric entity, a mathematical structure with physical consequences. It has shape, curvature, and dynamics. It can expand, it can ripple, it can contain singularities, it can hold horizons. What you experience as gravity is simply the way space-time guides objects along curved paths. There is no force pulling planets into orbit. They move naturally along geodesics. There is no force dragging you downward. The ground is pushing upward, preventing you from following your natural path. When you fall freely, you feel weightless because nothing resists your motion. Your senses misinterpret this as the absence of gravity, when in fact it reveals gravity's true nature, the geometry of space-time. The story of space-time becomes even more astonishing when you consider its origin. The universe began not in space but with space, not in time but with time. The Big Bang was not an explosion inside a pre-existing emptiness. It was the moment when space-time itself came into being. Asking what happened before the Big Bang misunderstands the nature of time, because before assumes a temporal structure that did not exist. Time itself had a beginning in the same way that a line has a starting point. The earliest moments of the universe set the shape of space-time, determining how galaxies would form billions of years later. Tiny fluctuations in the newborn universe became seeds of cosmic structure, stretched by inflation and sculpted by gravity. Everything you see, stars, planets, clusters, voids, emerge from this early geometry. Even now, space-time continues to change. The universe is expanding, not because galaxies are flying apart through empty space, but because space itself is stretching. Light traveling across billions of years is stretched along with it, lengthening into redder wavelengths. Distant galaxies recede, not because they move, but because the metric defining distances is evolving. Dark energy accelerates this expansion, influencing the large-scale fate of the cosmos. These effects challenge intuition because human experience is not built to perceive the expansion of space-time directly, yet they define the universe's history and future. Closer to home, space-time shapes Earth and everything on it. Without gravity, without curvature, there would be no atmosphere, no oceans, no mountains, no stable orbits, no seasons, no life. The sun shines because gravitational compression ignites nuclear fusion. Earth orbits the sun because space-time curves around the sun's mass. Tides rise and fall because the moon and sun shape Earth's gravitational field. Even your sense of direction depends on gravity pulling your inner ear's fluids downward. Life evolved within space-time, shaped by its geometry, dependent on its stability. Everywhere you look, space-time defines what is possible. Its geometry determines whether light can escape a black hole, whether galaxies cluster into filaments, whether stars collapse or explode, and whether the universe expands forever or collapses in the distant future. It sets the speed limit of the universe, defines causality, and establishes the boundaries of past and future. It hosts quantum fields that fluctuate constantly, filling what humans once thought was empty space with restless activity. Space is not a void. It is a stage where the deepest physical laws play out. And yet, despite its sweeping importance, space-time remains mysterious. Scientists still do not know what space-time is at the smallest scales. They do not know how to reconcile its smooth geometry with the grainy nature of quantum mechanics. They do not know whether space-time is fundamental or emergent. They do not know what lies inside singularities or how the universe began. The study of space-time sits at the edge of physics. balancing between what is known and what is yet to be discovered. This documentary begins by stripping away the comforting illusions of everyday experience and revealing the universe as it truly is. It follows the story of how humans discovered that space and time are not separate categories, but intimately woven together. It explores how relativity overturns centuries of assumptions, how light cones shape causality, how black holes distort space-time in extreme ways, how gravitational waves ripple across the cosmos, and how the early universe created the structure we see today. As you journey deeper into this story, each idea will reshape your understanding of reality, revealing that you are not just living in the universe, you are living inside space-time, carried along by its geometry, shaped by its curvature, and connected to everything else within its vast, dynamic fabric. By the time this story ends, space-time will not feel like a simple backdrop anymore. It will feel alive, structured, and essential. It will feel like the invisible architecture that holds the cosmos together. You will see that your life is not a series of events floating in emptiness, but a continuous path written into space-time. And once you understand that, the universe and your place within it will never look the same again. Everything you have ever known, every star, every galaxy, every atom in your body, comes from an origin so strange and so unlike anything in human experience that the mind struggles to form a picture of it. The universe began not with a thunderous explosion, but with the birth of space-time itself. There was no darkness before it because there was no space. There was no stillness before it because there was no time. There was no void, no background, no stage waiting to be filled. The Big Bang was not an event inside the universe. It was the event that created the universe. To understand space-time, you must begin with the moment when space-time itself came into existence. Imagine a state without dimension, without distance, without duration. This is not emptiness, it is the absence of a framework in which emptiness could exist. Human intuition tries to imagine before the Big Bang, but the idea dissolves on examination. Before requires time, and time did not exist. Outside requires space, and space was not there. What existed was a state that cannot be described in ordinary language, because language is built on temporal and spatial concepts. The best that science can offer is that the conditions of the early universe are encoded in the laws we observe today. What happened at the moment of creation remains one of the deepest mysteries in physics, but the consequences of that moment shape everything that followed. When space-time was born, the universe was unimaginably small, dense, and hot. Temperatures soared to levels where the physical laws we know today had not yet differentiated. Forces that are now distinct, gravity, electromagnetism, the nuclear interactions, were unified in ways scientists can only approximate through mathematics. Matter as we know it did not exist. Atoms, protons, neutrons, and even quarks were impossible. Instead, the universe was a storm of energy and primitive fields, fluctuating wildly due to quantum uncertainty. These fluctuations were not imperfections, they were seeds. They carried the imprint of randomness that would grow into the structure of galaxies billions of years later. Every cluster of galaxies, every star, every planet owes its existence to tiny quantum ripples in the earliest fractions of a second. The universe did not expand slowly or steadily in these early moments. Instead, it underwent a radical growth spurt known as inflation. In an instant far shorter than any human measure, the universe expanded exponentially. Distances that were smaller than a proton ballooned to cosmic scales. This expansion was not a movement through space, it was the stretching of space-time itself. Everything doubled in size repeatedly, faster than the speed of light, yet without violating relativity, because the expansion of space is not a motion within space. Inflation smoothed the universe, ironing out irregularities and erasing relics of earlier conditions. It stretched quantum fluctuations into macroscopic structures setting the stage for galaxy formation. Inflation ended, but the expansion continued, albeit at a slower pace. As the universe cooled, energy condensed into particles. Quarks formed protons and neutrons. These combined into atomic nuclei. Later, electrons joined to create atoms, releasing the first light that could move freely through space. This light still fills the universe today as the cosmic microwave background, a faint and nearly uniform glow carrying within it the imprint of early fluctuations. When scientists study this radiation, they are looking at a snapshot of spacetime when it was only 380,000 years old. Patterns in this glow reveal how matter was distributed and how spacetime behaved shortly after its birth. The cosmic microwave background is one of the clearest windows into the early universe. It shows that spacetime was smooth on large scales, but carried tiny variations, density differences of about 1 part in 100,000. These ripples were enough to allow gravity to begin shaping structure. Regions slightly denser than average slowed the expansion locally, drawing in matter and forming the first gravitational wells. Over time, these wells deepened, pulling more material into clumps that eventually became galaxies and stars. Without these early ripples, the universe would be perfectly uniform, filled with diffuse gas and devoid of structure. Ironically, the universe owes its complexity to minute imperfections born from quantum uncertainty. Even the concept of scale behaves differently in the early universe. Distances had no fixed meaning when spacetime was extremely curved. The idea of an edge or center of the universe is misleading. The Big Bang happened everywhere at once, because spacetime itself expanded from every point. There is no location you can point to and say, this is where it started. Just as all points on the surface of a balloon move outward during inflation, so too did all regions of the universe expand from one another. The expansion is not pushing galaxies apart. Space is stretching and carrying them with it. This stretching continues today. Galaxies recede from one another, not because they're flying through space like debris from an explosion, but because the metric that defines distances is evolving. The larger the distance between galaxies, the faster they appear to recede. This relationship, Hubble's law, is not about velocity, but about the expansion of the underlying spacetime. Light traveling across the universe is stretched along with the expansion, shifting into redder wavelengths. When you look at distant galaxies, you're seeing them not as they are today, but as they were billions of years ago, when the universe was younger, smaller, and denser. Dark energy complicates this picture further. In the late 20th century, scientists discovered that the expansion of the universe is accelerating. Something is pushing space to expand faster over time. This mysterious component, called dark energy, does not clump like matter and does not behave like radiation. It acts as a property of spacetime itself. Its nature remains unknown, but its effects are profound. It determines the future of the universe. If dark energy remains constant, the universe will expand forever, growing emptier as galaxies drift beyond one another's sights. If it grows stronger, a speculative but not impossible scenario, the universe could tear itself apart in a distant Big Rip. If dark energy weakens or reverses, expansion could halt or collapse into a big crunch, though current data favors eternal expansion. Understanding these possibilities requires recognizing that spacetime is not static. It evolves, it stretches, it responds to the energy and matter within it. The idea of a fixed cosmic arena has been replaced by the idea of a dynamic, responsive fabric. This fabric governs the motion of everything that exists, from photons to planets to clusters of galaxies. It determines what paths objects can follow, how light travels, how time flows, and how structures emerge. It sets the limits of causality, what events can influence one another, and what events lie forever beyond communication. The philosophical consequences are just as deep as the scientific ones. If time began at the Big Bang, what does it mean for something to exist? If space is stretching, what does it mean for something to move? If space-time can ripple, what does it mean for distance itself to change? These questions may sound abstract, but they highlight the difference between ordinary experience and cosmic reality. Humans perceive space and time through senses shaped by evolution on a stable planet in a weak gravitational field. But the universe is not bound by intuition. It behaves according to laws that extend beyond human experience. The early universe also raises questions about causality. Inflation expanded space-time so rapidly that regions now visible on opposite sides of the sky were once close enough to influence each other. Without inflation, the universe would contain isolated patches with different temperatures and densities, but observations show remarkable uniformity. Inflation explains this by allowing information to spread before being stretched beyond communication. As strange as it sounds, the smoothness of the cosmos requires space-time to have been extremely small and tightly connected before expanding faster than light. This does not violate relativity because nothing traveled through space-time faster than light. Instead, space-time itself expanded. Another surprising feature of the early universe is how quickly symmetry broke. At high energies, the fundamental forces were unified, but as the universe cooled, they separated into gravity, electromagnetism, and the nuclear forces. This symmetry breaking determined the structure of atoms and the interactions that make chemistry and life possible. Tiny differences in how these forces emerged had enormous consequences. A slightly different pattern of breaking could have created a universe without stable atoms or stars. This sensitivity raises deep questions. Why these laws and not others? Why this space-time geometry instead of another? These questions remain open, though they belong partly to metaphysics as well as physics. As the early universe evolved, matter and radiation interacted intensely. Photons scattered constantly off free electrons, preventing light from traveling far. Only when the universe cooled enough for electrons to bind with nuclei did the cosmos become transparent. From that moment onward, light traveled freely, carrying messages from the past. That ancient light now forms the cosmic microwave background, a relic of the universe's childhood. Studying its patterns reveals the shape of space-time when everything was still young. It shows how matter was distributed, how the universe expanded, and how inflation sculpted the earliest structures. The early universe also created the first elements. In the first few minutes, protons and neutrons fused into hydrogen, helium, and trace amounts of lithium. These primordial elements filled the cosmos long before stars existed. Later, gravity gathered these elements into clouds, igniting nuclear fusion and forming the first stars. In their cores, heavier elements were forged, eventually seeding planets, oceans, and life. All of this happened because space-time evolved in a way that allowed complexity to arise. If the expansion had been too fast, matter would never have clumped. If it had been too slow, the universe would have collapsed before stars could form. The balance between expansion and gravity, between the stretching of space-time and its curvature, determined whether the universe would be empty, chaotic, or structured. Today, remnants of the early universe still influence everything. The distribution of galaxies reveals the imprint of primordial fluctuations. The expansion rate records the effect of dark energy. The curvature of space-time determines the behavior of gravity across cosmic scales. Even the flow of time depends on the geometry set in motion by the Big Bang. Every moment you live takes place in a universe shaped by conditions established billions of years ago. You are not separate from this story. You are a continuation of it. The birth of space-time is not merely an event in the distant past. It is the foundation upon which reality stands. It set the rules for how time flows how distances change, how matter behaves, and how structure emerges. It is the starting point for everything you will explore in this documentary, and once you understand how space-time began, you will see that the universe is not a place you occupy. It is a dynamic fabric you inhabit, woven through with energy, curvature, expansion, and possibility. For most of human history, space and time seemed so simple that almost no one questioned their nature. They were treated as obvious truths, the kind that required no explanation. Space was imagined as an infinite, unchanging arena where everything happened. Time was imagined as a universal rhythm, flowing steadily forward from past to future. The same for every person, every place, every moment. These ideas feel comfortable because they align with everyday experience. When you walk across a room, the floor beneath you does not stretch. When you leave your home and return later, the building has not aged at a different rate from you. Our senses teach us that space is a constant background and time is an absolute flow. This classical picture of reality became so deeply rooted in human thought that it influenced philosophy, religion, art and science for centuries. But it was a picture built from intuition, not from nature. Long before modern science, Greek thinkers proposed early frameworks. Euclid, around 300 BCE, described space using geometry, lines, angles, planes, treating it as perfectly straight and infinitely extendable. His geometry became the language through which people imagined the world. Aristotle believed time was simply the measure of change and motion. These ideas became accepted largely because people lacked the tools to test them. They felt correct. They worked well enough for daily life. But intuition, no matter how compelling, is not the same as truth. The classical worldview took its most influential form in the 17th century with Isaac Newton. To humans who lived before Einstein, Newton's vision of space and time felt like the final word, clear, logical, and powerful enough to explain the motion of planets and falling apples with the same equations. Newton imagined space as absolute, a fixed, immovable, eternal stage that existed independently of anything inside it. No matter what happened, the geometry of space remained unchanged. Time was absolute as well, a universal flow that marched forward at the same rate everywhere, unaffected by motion or gravity. Newton described time as if it were a perfectly synchronized cosmic clock, ticking identically for all observers at all locations throughout the entire universe. This framework revolutionized science. It allowed for precise predictions of planetary orbits, tides, and celestial motion. It provided the foundation for classical mechanics, which remains extraordinarily useful today. But despite its power, Newton's picture contained silent assumptions that would eventually collide with deeper truths. The first cracks appeared in ways so subtle that only careful mathematical study could reveal them. One of Newton's assumptions was that objects moved because forces acted upon them. Gravity, in his view, was an instantaneous attraction that followed a simple inverse square law. Masses pulled on one another across empty space, and this pull could be calculated precisely. But Newton himself was uneasy about this idea. How could one object exert a force on another with nothing in between? What was the mechanism? He famously admitted that he did not know. Action at a distance felt mysterious even in his own era. Another problem came from the idea of absolute motion. Newton believed that acceleration could be measured against absolute space. He argued that even if you were inside a sealed box with no windows, you could detect whether you were rotating by observing how objects behaved inside. This was his way of saying that space itself provided a fixed frame of reference. But this concept clashed with the idea that the laws of physics should be the same no matter where you are or how you move. Why should the universe privilege one frame of reference over another? The question lingered unanswered. For centuries, Newton's view held strong because nothing seemed to contradict it. But as scientists probed nature more deeply, small inconsistencies appeared. One of the most important came from the study of light. Experiments showed that the speed of light was the same regardless of the motion of the source or observer, something classical physics could not explain. If space and time were absolute, the speed of light should vary depending on motion, but nature refused to obey that rule. Light behaved in ways that did not fit the classical picture. Another challenge came from Maxwell's equations of electromagnetism. These equations described how electric and magnetic fields interact, and they implied that light was a wave traveling at a fixed speed. But waves usually require a medium to travel through, a substance that oscillates. Sound waves require air. Water waves require water. Classical physicists assumed that light required a medium too, and they called it the luminiferous ether. This ether was imagined as a substance filling all of space, rigid enough to carry light waves, yet imperceptible to all other experiments. It was the perfect example of a concept invented to preserve an old idea rather than describe reality. Decades of attempts to detect the ether failed. The most famous test, the Michelson-Morley experiment, found no evidence at all for the ether's existence. Light simply did not behave as classical space and time demanded. The universe was sending a message. Space and time were not the simple absolutes humans believed them to be. Yet many scientists resisted the idea. It is difficult to abandon a framework that works so well and feels so intuitive. But science progresses not by clinging to intuition, but by confronting its failures. Another deep crack appeared in astronomy. Newton's equations predicted planetary orbits with astonishing accuracy, but one orbit didn't quite fit. Mercury, the innermost planet, precessed around the Sun slightly faster than expected. The discrepancy was small but persistent. For decades, scientists attempted to explain this by adding unseen planets or making small adjustments to Newton's laws. None of these fixes worked. The orbit of Mercury became a clue, a whisper that something in classical spacetime was incomplete. Human intuition was also challenged by the idea of simultaneity. Before Einstein, people assumed that if two events happened at the same time, they were simultaneous everywhere in the universe. But this assumption depended on absolute time, Newton's universal clock. Without it, simultaneity becomes ambiguous. The idea that two observers moving differently could disagree about which events happened simultaneously did not fit into the classical worldview. Yet this disagreement is not only possible, but necessary to explain how the universe actually behaves. The dream of an absolute, unchanging space also faltered when scientists considered the behavior of inertia. Why do objects resist changes to their motion? Newton described inertia mathematically, but could not explain its origin. This led to philosophical debates, including Mach's principle, which argued that inertia might arise from the relationship between an object and the mass of the entire universe. This radical idea implied that space was not an empty stage, but a structure influenced by everything within it. Although Mach's principle remains partly speculative, it pointed in a direction that Newton's framework could not accommodate. As these cracks grew wider, the classical picture of space and time began to bend under its own contradictions. Yet no one could abandon it without something better to replace it. For nearly 2 centuries, physicists struggled with the tension between the intuition that space and time were absolute and the experimental evidence suggesting they were not. It was a problem too big for patchwork solutions. Then came Einstein, who realized that the problem was not with the experiments. It was with the assumptions. Humanity had been trying to squeeze the universe into a framework that did not match reality. The universe was not wrong. Human intuition was. But before Einstein could unify space and time, before he could show that gravity was geometry, the world had to reach a point where the classical picture was already ready to break. Each inconsistency, light's constant speed, the failure of the ether, the inertia problem, Mercury's orbit, the relativity of simultaneity, acted like stress lines in a shell, and eventually that shell cracked open. Even before Einstein, hints of relativity began to appear. Lorentz and Poincaré developed mathematical transformations that preserved the speed of light, but they still believed in absolute time. Their equations worked, but their interpretation did not match physical reality. They bent mathematical rules to fit classical thinking, while Einstein broke classical thinking to fit the rules. By the early 20th century, space and time were ready for a revolution. Classical physics had taken humanity far, but it could not go further without collapsing under its contradictions. The universe demanded a new perspective, one that would reveal space-time not as a static stage, but as a dynamic entity. Newton's view was not wrong. It was incomplete, a special case that applied only under limited conditions. At low speeds, weak gravity, and small distances, it worked beautifully. But the universe is not limited to those conditions. Before Einstein, humanity's greatest mistake was assuming simplicity where nature had woven complexity. Classical space was simple, Euclidean, flat, and eternal. Classical time was steady, uniform, and absolute. Classical gravity was a force transmitted instantly. These ideas endured not because they were correct, but because they were comfortable. When Einstein shattered this comfort, he revealed a universe far richer than imagination, a universe where space and time warp, where clocks disagree, where geometry guides motion, and where the very fabric of reality can stretch and ripple. But before that revelation, the classical worldview had to be acknowledged for what it truly was, a stepping stone, not the destination. And with its limitations exposed, the stage was set for one of the most profound transformations in scientific history, the arrival of space-time as the true framework of reality. The moment Einstein entered the story of physics, the universe changed. Not physically, the cosmos continued as it always had, but intellectually, human understanding cracked open in a way that would never close again. Before Einstein, the world seemed governed by common sense. After Einstein, common sense no longer applied. Space and time were not isolated realms. They were not absolute. They were not fixed. They were not passive. They intertwined, bent, stretched, and responded to motion and energy. This shift in perspective was not a small correction or a modest refinement. It was a total reconstruction of the foundation on which physics had stood for centuries. Einstein began by questioning something so basic that almost no one thought to doubt it: the experience of time. Under classical assumptions, time flowed steadily for everyone, but the experimental evidence surrounding light contradicted this. If the speed of light was the same for all observers, no matter how fast they moved, then classical time could not be correct. Something had to give. Most scientists attempted to modify electromagnetism or invent hidden mechanisms. Einstein instead removed the assumption that time was absolute. He eliminated the idea that the universe needed a universal clock. He allowed time itself to change depending on motion. This step was so radical that even Einstein later remarked how astonishing it felt. It was not mathematics alone that led him to this insight. It was a willingness to abandon intuition when intuition no longer matched nature. He imagined what it would be like to chase a beam of light. If he moved faster and faster, approaching the speed of light, would the light appear to slow down? The answer, based on experiments, was no. Light would always travel at the same speed relative to him. This meant motion through space must alter motion through time. As you move faster, you consume some of your allowance of motion through time. Time itself must slow down for you. This simple but profound idea became the seed of special relativity. Einstein proposed that the laws of physics are the same in all inertial frames, and that the speed of light in vacuum is constant for all observers. From these two principles, all the counterintuitive consequences of relativity emerged naturally. Time dilation allows moving clocks to tick slower. Length contraction shortens objects along the direction of motion. Simultaneity becomes relative, meaning two events that seem simultaneous to one observer may not be simultaneous to another. The universe does not provide a single slice of now that everyone shares. Instead, each observer carries their own notion of present, shaped by their motion. This realization is not merely philosophical, it is embedded in the structure of space-time. If two lightning bolts strike different ends of a moving train, an observer on the train may see one bolt before the other, while an observer on the ground may see them as simultaneous. Neither perspective is wrong. The disagreement arises because simultaneity is not absolute. The order of events can depend on the observer's motion. This shatters the classical idea of universal time and shows that the flow of events is entwined with the geometry of space-time. The structure that replaces classical space and time is a unified four-dimensional continuum. Space has three dimensions, time has one, and together they form space-time. An event in the universe is located not only by where it occurs, but also by when. The separation between events depends on the observer's state of motion. Distances in space and intervals of time can transform into each other. They are not independent quantities, but components of a single geometric entity. Minkowski, Einstein's former mathematics teacher, articulated this elegantly by saying that space and time are doomed to fade into shadows, and only a union of the two will preserve an independent reality. Though Einstein initially resisted this geometric interpretation, he soon recognized its power. Once spacetime becomes the stage, the laws of physics take on a new clarity. The path of a particle through the universe becomes a world line. The length of a world line becomes the proper time experienced by the particle. Motion through space reduces motion through time, and vice versa. Light, which travels at the maximum possible speed, experiences zero proper time between emission and absorption. To a photon, the universe has no duration. In this framework, inertia becomes a geometric property. An object not acted upon by external forces travels along a straight path through spacetime, a geodesics. In flat spacetime, geodesics are straight lines. But if spacetime is curved, the straightest possible path may appear bent when projected onto three-dimensional space. This insight laid the groundwork for Einstein's next leap, the recognition that gravity is not a force at all, but a manifestation of curvature. Before Einstein reached that point, he first needed to understand how acceleration behaves in relativity. He imagined two scenarios, one where a person stands on Earth feeling the weight of gravity, and another where a person stands in a rocket accelerating upward in deep space. In both cases, the person feels a force pushing them against the floor. The sensations are identical. This equivalence between gravitational acceleration and inertial acceleration became the key to unlocking gravity's true nature. If you cannot distinguish between standing on the ground and accelerating upward, then perhaps gravity is not a separate force. Perhaps it arises from the structure of spacetime itself. But this insight would not bloom until Einstein tackled the limits of special relativity. Special relativity applied only to observers moving at constant velocities. But the real universe contains accelerations, rotations, gravitational fields, and curved trajectories. Einstein sought a theory that could incorporate all motion, not just uniform motion. This desire led him to general relativity. Before he could reach general relativity, though, he needed to question every assumption about space and time. He realized that space could no longer be a rigid framework. If time dilates and lengths contract depending on motion, then geometry itself cannot be fixed. The presence of energy must influence the structure of space-time. He also realized that the force of gravity acts universally on all forms of mass and energy, and the only thing universal enough to replace a force is the geometry experienced by all objects. This made gravity a geometric property of spacetime rather than an interaction transmitted across distance. But Einstein did not arrive at general relativity suddenly. It took years of struggle with equations, geometry, and conceptual obstacles. He had to abandon Euclidean geometry and embrace non-Euclidean spaces where straight lines curved and angles did not sum to 180 degrees. He had to accept that coordinate systems could not define reality. Only invariants, quantities that all observers agree upon, could describe nature. He had to refine the concept of an inertial frame, recognizing that local inertial frames exist even in curved spacetime, allowing freely falling observers to experience gravity-free motion. These ideas were so revolutionary that they challenged not only physics, but human perception. People think of space as a container. They think of time as a flow. They think of motion as something that can be measured independently of the observer. Einstein showed that all of this was wrong. Motion is relative. Time depends on velocity. Distances depend on frames of reference. And space and time cannot be separated from one another. This unification transformed the way scientists understood energy, momentum, and causality. The equations governing them became symmetric and elegant. The conservation laws of physics became geometric truths. The famous equation E mc2 emerged naturally from the structure of spacetime, showing that mass and energy are different expressions of the same thing. This equation is not merely a formula, it is a statement about how spacetime responds to matter and energy. Einstein's revolution also redefined how information moves through the universe. Nothing can exceed the speed of light, because doing so would require moving outside the structure of spacetime's causal boundaries. Light cones, those geometric shapes showing which events can influence others, became central. They determine which events lie in your future and which lie in your past. They define the limits of possibility. If an event lies outside your light cone, no signal can reach you from it, no matter how advanced your technology becomes. Space-time itself enforces causality. This perspective replaced the classical idea of absolute simultaneity. Now, events become connected or disconnected depending on geometry. This structure influences everything from particle physics to cosmology. It explains why certain processes occur in one frame but appear different in another. It shows how time travel is constrained, how motion warps time, and how energy flows through the universe. Einstein's revolution did not stop with special relativity. It opened the door to general relativity, which would show that space-time is not only a stage but an actor. The fabric of reality bends in response to energy and mass. Gravity becomes geometry. Freefall becomes natural motion. The shape of space-time becomes the script for the universe. But none of that could happen without first realizing that space and time are not separate elements. They're a unified continuum where motion, time dilation, length contraction, and the relativity of simultaneity all arise naturally. Einstein took the most familiar aspects of human experience, space and time, and revealed them to be illusions of simplicity. Beneath those illusions lies a structure richer, deeper, and more intricate than the classical world could ever contain. He did not change the universe, he changed our ability to perceive it. And with the unification of space and time complete, the next step was inevitable. Discovering how gravity fits into this new geometric reality, a journey that would lead to one of the greatest scientific achievements in human history. If you want to understand gravity the way Einstein understood it, the first thing you must abandon is the idea that falling means being pulled downward. Falling is not a force dragging you. Falling is not a failure of support. Falling is not even motion caused by gravity. Falling is the purest expression of moving naturally in space-time. To fall freely is to follow the path that space-time lays out for you, the path of least resistance, the straightest possible world line. It is what an object does when nothing interferes with it. And paradoxically, it is also the state in which you feel no gravity at all. You float, weightless, not because gravity is absent, but because nothing is pushing back against the geodesic that space-time demands you follow. This idea is so different from everyday intuition that it takes time to settle into the mind. People associate weight with the pull of gravity. They imagine that standing on the ground means gravity is acting on them, and floating in orbit means gravity has disappeared. But the truth is the opposite. When you stand on the ground, gravity is trying to make you fall. The only reason you do not fall is because the ground exerts an upward force, pushing on your feet, compressing your bones, creating tension in your muscles. That upward push is what you feel as weight. Weight is not the presence of gravity, it is the resistance to gravity. Gravity wants you to fall along your geodesic, but the ground refuses to let you. When that resistance disappears, when nothing pushes up on you, you feel weightless, even though gravity still governs your motion completely. This realization grows even more powerful when you consider astronauts in orbit. They float not because Earth's gravity is weak at their altitude. Gravity at the International Space Station is about 90% as strong as it is on the ground. They float because they are in continuous free fall around the Earth. Their sideways velocity carries them forward at the same rate that Earth curves beneath them. They are always falling but never landing. Every object inside the spacecraft follows the same geodesic. So there is no resistance, no compression, no pressure upward. And with nothing pushing back, the sensation of weight vanishes. What people call zero gravity is really zero support force. Einstein recognized that the experience of freefall contained the key to understanding gravity itself. If a person in a falling elevator feels weightless and a person floating in deep space also feels weightless, then these two situations are physically equivalent. The laws of physics behave the same way in a small region of freefall, regardless of whether the motion arises from gravity or inertial motion. This deceptively simple insight became the cornerstone of Einstein's vision. He called it the equivalence principle, the idea that freefall is indistinguishable from inertial motion, and that gravity cannot be separated from the geometry of space-time. Imagine being sealed inside a room, completely isolated from the outside world. If you are floating freely, you cannot tell whether you are drifting in empty space or falling toward a planet. If you are standing on the floor with a steady force pressing downward, you cannot tell whether you're on the surface of a planet or inside a rocket accelerating upward. The sensations are identical. The physics inside the room is identical. The distinction between gravity and acceleration dissolves. What remains is a geometric truth. Gravity acts like curvature because it is curvature. It is the result of following geodesics through a warped space-time. The idea of geodesics is central. In Euclidean geometry, a straight line is the shortest path between 2 points. In curved space-time, a geodesic is the path that requires no force to follow. It is the natural path an object takes when nothing pushes on it. In flat space-time, geodesics are straight world lines. In curved space-time, geodesics bend. They bend not because something pulls them, but because the underlying geometry curves. A freely falling object always follows a geodesic. A standing object does not. That is why you feel weight when standing and weightlessness when falling. Standing on the ground forces your world line to deviate from the path space-time wants you to take. This reframing transforms gravity from a force into a property of space-time. Mass and energy tell space-time how to curve, and space-time tells objects how to move. When Einstein realized this, he saw that gravity could be eliminated locally by choosing the right frame of reference. A freely falling frame experiences no gravity. A small enough region of space-time always looks flat to a free-falling observer. Gravity becomes a global effect, something that cannot be eliminated everywhere at once but can always be transformed away in a sufficiently small region. This is why astronauts float, why objects fall at the same rate regardless of their mass, and why gravity is so consistent across scales. The equivalence principle also explains why light bends near massive objects. Even though photons have no mass, they follow geodesics. If space-time is curved, the geodesics curve and the photons must follow. In a freely falling elevator, a beam of light drawn across the elevator appears straight, but to an outside observer watching the elevator fall, the beam appears to bend downward. Einstein realized that if acceleration causes light to bend for an observer inside an accelerating frame, then gravity must also cause light to bend. Light does not bend because gravity pulls on it. Light bends because space-time curvature changes what straight means. All these ideas require abandoning the classical belief that space is a static arena. Instead, space becomes something that can tilt, twist, and stretch. Time becomes something that can slow down or speed up depending on motion and gravitational potential. Together, they form space-time, a structure that determines every motion you ever make. To grasp this deeply, imagine an observer floating freely somewhere in space. Without external forces, that observer feels perfectly calm. Objects around them drift without resistance. If they release two balls side by side, both move parallel to one another, tracing straight lines in their immediate region. But if space-time is curved, those straight lines eventually converge or diverge. Two balls dropped toward Earth do not remain parallel. Their paths converge as they fall. This is not because the balls pull each other, but because they follow geodesics that naturally intersect due to curvature. Geodesic deviation, how nearby geodesics move relative to one another, reveals the curvature of space-time. This geometric viewpoint becomes the mathematical heart of general relativity. But before Einstein completed general relativity, he needed to understand how gravity affects time. The equivalence principle implies that clocks behave differently depending on their position in a gravitational field. A clock closer to a massive object ticks more slowly than a clock farther away. If you climb a mountain, you age slightly faster than someone at sea level. This effect is tiny in everyday life, but measurable with atomic clocks. Without correcting for it, GPS satellites would accumulate errors so quickly that navigation on Earth would become impossible. Gravity slows time because space-time curves. The flow of time is not absolute, it is shaped by geometry. Einstein also realized that gravity affects what observers consider vertical. In a free-falling frame, objects float because nothing pushes against them. In a non-free-falling frame, such as standing on Earth, the upward force from the ground defines what you perceive as downward, even though down is simply the direction in which space-time guides geodesics. If the floor vanished beneath you, you would not be pulled downward. You would simply stop being forced upward. You would follow your geodesic, the path that space-time defines as natural. These insights bring us closer to the geometric picture of gravity. To complete the transition, you need to consider how space-time treats different kinds of motion. Every object, from a thrown ball to a falling apple to a spinning planet, traces a world line. These world lines intersect, diverge, or run parallel depending on curvature. Causality emerges from the structure of light cones, regions of space-time, that determine what events can influence others. Light cones tilt and distort in curved space-time, reshaping what futures and pasts are possible. In a strong gravitational field, light cones tip inward, forcing all paths to point deeper into the gravitational well. This is why nothing can escape a black hole. Inside the event horizon, the light cones tip so steeply that all possible futures lead inward. All of this complexity arises naturally from the equivalence principle. By recognizing that freefall eliminates gravity locally, Einstein realized that gravity must be something more than a force. It must be the curvature of spacetime itself. Objects fall not because they're pulled, but because their geodesics lead toward mass. The curvature determines how geodesics intersect, diverge, or converge. It determines how time flows and how space stretches. It determines how light bends, how planets orbit, and how objects accelerate. This understanding makes gravity both simpler and more profound. Simpler, because it removes the need for unseen forces acting at a distance. More profound, because it reveals that the universe is not governed merely by forces and masses, but by geometry. You are not pulled toward Earth. You are guided by the shape of space-time. You are not held down by gravity. You are pushed up by the Earth. You are not separate from the cosmos. You are embedded within its curvature. Einstein's equivalence principle was the seed from which the full theory of general relativity grew. It provided the conceptual bridge between special relativity and the gravitational universe. It transformed gravity from a mysterious force into a geometric consequence of mass and energy. And with this bridge established, Einstein was now ready to reshape physics at its deepest level, revealing how mass curves space-time, how curvature guides motion, and how the universe's structure emerges from geometry itself. When Einstein finally completed his field equations, he did not just create a new theory of gravity. He created a lens through which the universe could be seen clearly for the first time. Before this moment, gravity was a force whose cause was unknown, a mysterious interaction acting across empty space. After Einstein, gravity became geometry. Mass and energy curve spacetime, and spacetime tells matter how to move. With this understanding, Einstein's equations did something extraordinary. They made predictions so bizarre, so counterintuitive, and so far beyond everyday experience that even Einstein at times doubted whether nature would allow such things to exist. Yet time after time, the universe confirmed the equations with remarkable precision. Each prediction became a window into a deeper layer of reality, revealing that space-time is far stranger and richer than anyone had imagined. One of the first predictions that emerged from Einstein's work was gravitational time dilation. The idea that time flows differently depending on where you are in a gravitational field. In Newtonian physics, time is absolute. It moves at the same rate everywhere, but Einstein showed that time is bound to the geometry of space-time. Where space-time is curved, clocks slow. Where the gravitational potential is higher, time flows faster. You are aging at a slightly different rate than someone standing above or below you. Every point on Earth experiences time differently, not metaphorically, but physically. The flow of time is not uniform. It bends according to gravity. This effect is so real that modern technology must account for it. The satellites in Earth's orbit, which carry the atomic clocks used for GPS, experience weaker gravity than clocks on Earth's surface. Their clocks tick faster. Without compensating for this difference, combined with the slowing caused by their orbital speed, GPS would drift by kilometers within a single day. Your phone only works because Einstein understood that time is malleable. Every route you navigate, every map you follow, every coordinate you receive is corrected for the bending of time by Earth's mass. The slowing of time near massive objects becomes extreme in strong gravitational fields. Near a neutron star or black hole, seconds can stretch into hours or years. An observer hovering close to a black hole's event horizon experiences time at such a slow rate that distant galaxies seem to evolve in fast forward. From the perspective of someone far away, the hovering observer appears to freeze in time, never quite crossing the horizon. These are not approximations, they are direct consequences of Einstein's equations. The universe allows time to stretch, twist, and slow until it nearly stops. If time behaves so strangely near mass, light behaves strangely as well. Einstein predicted that light would bend when passing near massive objects, not because gravity pulls on it, but because space-time curvature changes what a straight path means. Light always follows the straightest possible world line, but in curved space-time, straight lines curve. The bending of starlight around massive bodies became one of the earliest observational tests of general relativity. In 1919, during a total solar eclipse, starlight passing near the Sun appeared shifted from its normal position. The amount of bending matched Einstein's prediction precisely. It was a historic moment. Humanity had seen space-time curvature with its own instruments. This bending of light, known as gravitational lensing, has become one of the most powerful tools in modern astronomy. Massive galaxy clusters can bend light from galaxies behind them, creating arcs, rings, or multiple images. These distortions reveal the distribution of mass inside the cluster, including mass that emits no light. This is how scientists discovered dark matter on large scales. The visible matter in clusters is insufficient to produce the observed lensing. Something invisible must contribute to the curvature. Space-time itself became a detector for the unseen, allowing astronomers to map structures that no telescope could observe directly. Gravitational lensing also magnifies distant galaxies, making it possible to see objects formed shortly after the Big Bang. The universe uses space-time curvature as a natural telescope, revealing galaxies otherwise too faint to observe. When you look at those images, you're not only witnessing ancient light, you're witnessing the geometry of the universe, reshaping the path of that light. Curvature becomes a tool for discovery. As Einstein explored the implications of his equations, he encountered something even stranger: black holes, regions where curvature becomes so extreme that not even light can escape. The idea of a mass so dense that escape is impossible had existed since the 18th century, but Einstein's equations gave it a precise mathematical form. A sufficiently compact mass creates an event horizon, a boundary beyond which all world lines lead inward. Inside this horizon, space-time curves so sharply that the future of any object points inevitably toward the center. Nothing can avoid falling inward. Not particles, not light, not information. Einstein initially doubted that such objects could form in nature. They seemed too extreme, too mathematically pathological. But other scientists realized that his equations did not merely allow black holes. They predicted them as a natural outcome of gravitational collapse. When a massive star exhausts its fuel, its core collapses. If it becomes dense enough, not even neutron pressure can halt the collapse. The core compresses into a singularity, a point where curvature diverges and classical physics breaks down. The event horizon forms around this singularity, hiding it from the outside world. Black holes became one of the most dramatic predictions of general relativity. For decades they remained theoretical, but evidence accumulated slowly. X-ray emissions from binary systems, jet streaming from galactic centers, the orbits of stars around invisible objects. Eventually, the Event Horizon Telescope produced an image of the shadow cast by a black hole in the galaxy M87. This image, an orange ring surrounding a dark core, matched Einstein's predictions with astonishing accuracy. Another remarkable prediction emerged when scientists studied the effect of rotation on spacetime. A rotating mass drags spacetime around with it, twisting the geometry. This effect, called frame dragging, means that spacetime itself rotates near a spinning object. The effect is minuscule around Earth, but enormous near rotating black holes. In extreme cases, the dragging becomes so intense that nothing can remain at rest relative to the distant universe. All objects must rotate, swept along by spacetime's twist. This region, known as the ergosphere, becomes a realm where motion is dictated not by choice, but by geometry. Energy can even be extracted from this twisting, a process once thought purely theoretical but now considered seriously in astrophysics. These predictions did not arise from philosophical speculation. They emerge directly from Einstein's field equations, the mathematical statement that curvature equals matter and energy. Every test of general relativity has confirmed the equations to extraordinary precision. Gravitational redshift, time dilation, light bending, precession of planetary orbits, frame dragging, gravitational waves, all align with Einstein's predictions. The theory succeeded because it captures how space-time truly behaves. One of the most elegant predictions came from studying how space-time curvature affects orbital motion. Mercury's orbit had long deviated slightly from Newtonian predictions. Einstein's equations explained the discrepancy perfectly without any adjustments or additional planets. The curvature of space-time near the Sun caused Mercury's orbit to precess more than Newtonian physics allowed. This success convinced Einstein that his theory captured something fundamental. General relativity also predicted gravitational waves, ripples in space-time generated by accelerating masses. For a century, they remained undetected because the waves are extraordinarily subtle. But in 2015, the LIGO observatories recorded a tiny distortion in space-time caused by two black holes merging over 1 billion light-years away. The detectors measured a change in distance smaller than a proton's width. Yet this tiny signal carried the story of one of the most violent events in the universe. Gravitational waves opened a new window into space-time, allowing scientists to observe cosmic events that produce no light at all. Einstein's equations also reveal that space-time is dynamic. It evolves as the universe evolves. When matter clumps, curvature increases. When matter spreads out, curvature decreases. When energy dominates, expansion accelerates. Nothing in the universe is static. Even the emptiness of space is not empty. It contains vacuum energy, quantum fields, and fluctuations that influence the expansion of space-time. Einstein believed that the universe might be static, so he added a term to his equations, the cosmological constant, to counteract gravity. When Edwin Hubble discovered that the universe was expanding, Einstein reportedly called the constant his greatest mistake. Yet the constant returned decades later as the simplest explanation for dark energy. Einstein may have stumbled into predicting one of the universe's deepest mysteries. Despite its successes, general relativity contains puzzles. The theory predicts singularities, regions where curvature becomes infinite and the equations break down. It predicts horizons beyond which information cannot escape, raising questions about the nature of quantum mechanics. It predicts a universe that can expand, collapse, or evolve in ways classical physics never imagined. These predictions show the power of general relativity, but also hint that it is incomplete. Something deeper must exist beyond Einstein's equations, something that unifies geometry with quantum behavior. Yet for all its mysteries, general relativity remains the most accurate description of gravity ever created. When you watch a satellite orbit Earth, you're watching it follow a geodesic. When you drop a ball, you're watching space-time guide its motion. When you look at starlight bent by a galaxy, you are seeing curvature reshape the path of light. When you see the image of a black hole, you're seeing Einstein's geometry cast into the sky. General relativity did not merely improve our understanding of gravity, it transformed our understanding of reality itself. It revealed that the universe is not governed by forces acting at a distance, but by the shape of space-time. It showed that time flows differently depending on where you stand, that space bends under mass, that light follows curvature, and that the universe evolves dynamically according to its geometry. Each prediction not only matched observation, but expanded our sense of what is possible. And although these predictions were stunning, they were still only the beginning. The deeper implications of curvature, ripples, singularities, cosmic evolution, and the interaction between geometry and quantum fields would lead to even stranger discoveries as scientists probed the boundary between relativity and quantum mechanics. The beauty of any scientific theory is not in its elegance, but in its ability to predict reality with precision. Einstein's vision of spacetime curvature would have remained a philosophical curiosity if nature had not validated it at every turn. What makes general relativity extraordinary is how relentlessly the universe confirms it. Every experiment designed to test its predictions, whether performed on Earth, in orbit, or across billions of light years, reveals the same message. Space-time is curved, and this curvature shapes everything we observe. Even effects so small that no human could ever feel them still occur with unyielding consistency. Taken together, they form an overwhelming body of evidence that gravity is geometry, not force. One of the simplest and most direct tests came from examining the flow of time. General relativity predicts that clocks tick differently at different heights because of gravitational potential. Close to a massive object, time slows. Higher up, time speeds up. This is not metaphorical slowing, it is physical. If two perfectly identical clocks are separated by even a small change in elevation, they will drift apart. The effect is tiny, but measurable. In the 1960s, scientists used atomic clocks to prove this. They placed one on the ground and another on a tall tower. After running for hours, the clocks showed a difference, exactly equal to Einstein's prediction. Later, when clocks were flown around the world on airplanes, the measured time dilation matched both special and general relativity combined. Today, atomic clocks are so precise that raising one by even a few centimeters causes a detectable change in its ticking rate. You age faster standing on a stool than sitting on the floor, even if only by trillionths of a second. The universe does not care about human intuition. Time obeys space-time geometry alone. A second line of evidence comes from the bending of light near massive bodies. When starlight grazes the edge of the sun, its path curves slightly. This bending cannot be explained by Newtonian physics, which predicts only half the amount of curvature that occurs. In 1919, during a total solar eclipse, astronomers captured images of stars near the sun's limb. Their apparent positions were shifted exactly as general relativity predicted. This single observation catapulted Einstein to global fame. Newspapers declared a revolution in science, but the truth was far deeper. Humanity had witnessed space-time curvature with their own telescopes. Since then, this light-bending effect has been confirmed repeatedly, using radar signals bounced off planets, radio waves passing by galaxies, and high-resolution measurements from space probes. Each test reaffirms that mass bends the path of light because it bends the geometry through which light travels. Perhaps the most direct, everyday demonstration of space-time curvature comes from the GPS system. Satellites orbit Earth at high speeds and high altitudes. Their clocks run faster due to weaker gravity and slower due to special relativity's motion effects. The combined difference is about 38 microseconds per day. If these relativistic corrections were ignored, GPS positions would drift by kilometers daily, making the system unusable. Engineers must apply Einstein's equations continuously to keep the system accurate. This means that every time you navigate to a destination, you rely on general relativity to know where you are. Gravity's curvature of time is embedded in the infrastructure of modern society. Space-time curvature also reveals itself in the motion of planets. Mercury's orbit puzzled astronomers for decades because its perihelion, the point closest to the Sun, shifted slightly faster than Newton's laws predicted. Attempts to explain this by postulating another planet or modifying Newtonian gravity failed. But Einstein's equations predicted exactly the observed discrepancy. The intense curvature of spacetime near the Sun causes Mercury's orbit to precess by a small but measurable amount. This was one of the earliest triumphs of general relativity, and it remains one of the most precise confirmations ever recorded. No alternative theory without spacetime curvature has explained it successfully. Another piece of evidence comes from gravitational redshift, the stretching of light as it climbs out of a gravitational well. A photon, escaping a massive object, loses energy. It cannot slow down, so it shifts to a longer wavelength. This effect was first observed in laboratory experiments in the mid-20th century. Scientists measured the frequency shift of gamma-ray photons sent up and down a tall tower. The observed change matched Einstein's predictions perfectly. Later, the effect was measured astronomically in the spectra of white dwarf stars, where gravity is far stronger. The observed redshift again matched general relativity with extraordinary precision. The curvature of spacetime also reveals itself in less intuitive ways, such as the way massive rotating bodies drag spacetime around with them. This effect, called frame dragging, was measured by the Gravity Probe B satellite. The experiment used ultra-precise gyroscopes to detect minute changes in orientation caused by Earth's rotation twisting spacetime. The measured twist, measured in fractions of milliseconds, matched Einstein's predictions within experimental error. The Earth is not merely rotating in space, it is dragging spacetime along with it. One of the most visually striking confirmations of spacetime curvature comes from gravitational lensing on cosmic scales. Massive galaxy clusters warp the space around them so strongly that they act like giant lenses, bending and distorting the light from more distant galaxies. These distortions create arcs, rings, and multiple images. The universe becomes a natural funhouse mirror, but unlike a mirror, it reveals the presence of invisible mass. The lensing cannot be explained by visible matter alone. Something unseen, dark matter, contributes to curvature. By mapping the distorted shapes of gravitational lenses, astronomers can reconstruct the distribution of mass in galaxy clusters, including the dark matter that produces no light. The fact that general relativity predicts these lensing patterns so accurately is one of the strongest pieces of evidence for both spacetime curvature and dark matter's existence. Even more dramatic confirmations come from observations near black holes. The orbits of stars around Sagittarius A, the supermassive black hole at the center of the Milky Way, follow paths predicted by general relativity down to scales of mere light hours from the horizon. These stars move so rapidly and so closely that their motion provides a laboratory for testing gravity in extreme regimes. Measurements show that their orbits precess, their time dilation matches predictions, and their trajectories align with Einstein's equations with nearly perfect fidelity. In recent years, astronomers even detected the relativistic redshift in these stars' light as they approached perihelion. Each measurement reaffirms that spacetime near a massive object behaves exactly as predicted. Then came the Event Horizon Telescope images, snapshots of spacetime curvature made visible. The glowing rings seen around the black hole in M87 and around Sagittarius A are not artistic interpretations, but reconstructions from real data. The dark shadow at the center is the silhouette of the event horizon, shaped by photons orbiting in a photon sphere, all dictated by Einstein's geometry. The size of the ring, the brightness asymmetry, and the shadow's shape all match general relativity with astonishing precision. Humans have seen the shape of spacetime itself. Still another triumph came from gravitational waves, ripples in spacetime emitted when massive objects accelerate violently. Predicted by Einstein a century before detection, these waves remained elusive because their effects are incredibly small. But when LIGO and Virgo observed the first gravitational wave signal in 2015, the detection confirmed that spacetime does not merely bend, it flexes. Two black holes spiraled toward each other, merged, and shook the fabric of spacetime, sending waves across the cosmos. LIGO measured distortions thousands of times smaller than a proton, yet the signal matched Einstein's predictions in frequency, amplitude, and waveform. Since then, dozens of gravitational wave events have been detected, including neutron star mergers that produced both gravitational and electromagnetic signals. These detections allow scientists to observe space-time in motion, not through its static curvature, but through its dynamic vibrations. The universe also tests general relativity in environments where gravity is weak. Pulsars, which act as cosmic clocks, provide exquisite tests of gravitational effects. In binary systems, timing the pulses reveals how space-time curvature affects orbital motion. The Hulse-Taylor binary pulsar showed that the orbit shrinks at a rate exactly matching energy loss due to gravitational waves. This indirect evidence for gravitational radiation was so compelling that it earned a Nobel Prize decades before direct detection was possible. More recently, pulsar timing arrays have started detecting gravitational waves from supermassive black hole binaries across the universe, confirming that space-time is constantly trembling on vast scales. Even the expansion of the universe confirms the geometric nature of space-time. Hubble's discovery that galaxies recede from us at speeds proportional to their distance is not evidence of motion through space, but of expanding space-time itself. Supernova surveys in the late 1990s revealed that this expansion is accelerating. This unexpected result led to the concept of dark energy, which acts as a property of space-time rather than a form of matter. Space-time expands not because galaxies push outward, but because the fabric of the universe stretches. Everywhere scientists look, planetary motion, clock synchronization, light paths, cosmic evolution, black holes, gravitational waves, satellite technology, they find space-time curvature. No experiment contradicts general relativity. No measurement has yet revealed a violation. Even attempts to find deviations in strong gravity environments, such as neutron star collisions or the shadow of black holes, produce results that match Einstein's predictions. Space-time curvature has become one of the most robustly verified ideas in all of science. Despite its precision, general relativity is not complete. It does not describe quantum behavior. It predicts singularities that defy physical interpretation. It suggests that space-time can tear or stretch endlessly. These mysteries point to a deeper theory waiting to be discovered. But whatever new theory emerges, it will have to match general relativity in all the domains where it has been tested. Einstein's description of curvature will remain the classical limit of whatever quantum theory eventually replaces it. The evidence for space-time curvature is overwhelming because the universe itself performs the experiments. Every star orbiting a black hole, every photon bending around a galaxy, every gravitational wave crossing the cosmos, every satellite circling Earth, every precise atomic clock running anywhere in the world, all participate in confirming general relativity. The universe does not merely allow curvature, it displays it in every corner, every moment, every observation we are capable of making. Human beings believe they understand time because they experience it every moment. You feel the flow of seconds, the movement of the present into the future, the memory of moments that have already passed. You sense time as something continuous, irreversible, and universal. But these feelings are products of perception, not reflections of reality. When examined through the lens of physics, time behaves in ways so alien to intuition that even experienced scientists struggle to internalize them fully. Time does not flow at the same rate everywhere. It does not agree between observers. It does not connect events in a simple linear chain. It is not absolute. It is woven into the geometry of space-time, and that geometry can stretch, twist, tilt, or compress the temporal dimension in ways that defy expectation. The first break with classical intuition comes from the relativity of simultaneity. People assume that if two events occur at the same time, such as two lamps switching on, they are simultaneous for everyone in the universe. But simultaneity is not a fundamental property of reality. It depends entirely on the observer's motion. Two events judged to occur at the same moment, in one frame of reference may occur at different times for another observer, moving relative to the first. This is not a matter of perception or signal delay. It is built into the structure of space-time itself. Once you accept that simultaneity is relative, the entire idea of a universal now collapses. The universe does not provide a single shared present. Each observer carries their own slice of time, and those slices tilt relative to one another depending on motion. This tilting is not a metaphor, but a geometric consequence of space-time. When you move faster, your direction in space-time changes. Your time axis and space axis mix. You age differently, and your notion of simultaneity shifts. This is why a fast-moving observer sees distant clocks ticking at different rates. It is why two watchers traveling in opposite directions may disagree about which events in distant galaxies occur first. This disagreement is not an illusion. It is a fundamental feature of space-time geometry. With the relativity of simultaneity established, the next surprising behavior of time emerges from kinematic time dilation. When you move close to the speed of light, time slows down for you relative to those who remain at rest. Your heartbeat slows, your aging slows, your biological processes slow. Yet from your perspective, nothing changes. Your own time still feels normal. You do not sense your clock ticking more slowly. It is only when you compare your time to someone else's that the difference becomes apparent. In everyday life, where speeds are low compared to light, this effect is invisible. But in high-energy particle accelerators, time dilation is dramatic. Particles that should decay almost instantly survive far longer when moving at relativistic speeds. Their extended lifetimes are direct evidence that time itself is distorted by motion. Gravity warps time as well. Near a massive object, time flows more slowly. This gravitational time dilation has been verified repeatedly with atomic clocks on mountains, skyscrapers, airplanes, and satellites. Even a height difference of a few centimeters produces a measurable shift. That means the space within your own body contains a gradient of time, with your head aging slightly faster than your feet. This effect is too small to influence daily life, but it is real and persistent. It shapes the behavior of GPS satellites, influences the motion of planets, and becomes extreme near dense astrophysical objects. The extreme case appears near black holes. As you approach a black hole's event horizon, time slows more and more relative to a distant observer. To an outside viewer, you appear to freeze at the horizon, your clock ticking infinitely slowly. From your own point of view, however, you continue falling normally, experiencing time at its usual pace. This divergence is one of the strangest features of space-time. Two observers can have radically different experiences of time and both be correct within their own frames. Reality does not pick one perspective as more fundamental. Space-time accommodates both. These distortions of time lead naturally to the idea of the block universe, a way of describing space-time in which past, present, and future all exist together as part of a four-dimensional structure. In this view, there is no universal flow of time. The sense of movement from past to future is a feature of consciousness, not physics. Just as all locations in space coexist, all moments in time coexist. You experience them sequentially only because of the biochemical processes in your brain, not because the universe is unfolding. The present is not something that moves. It is a perspective tied to your world line. Different observers have different presents, different divisions between past and future, depending on their motion. This does not make time unreal. It makes time relational. It is tempting to think that the block universe eliminates change, but it does not. Change is encoded in the structure of space-time. Events follow one another along world lines. Processes unfold, particles decay, stars form, shine, and die. What the block universe removes is the idea of a universal now. Instead, it replaces it with the geometry of events, connected by causal relationships. This geometry preserves everything that actually occurs while removing the illusion of absolute simultaneity. The relativity of time also raises profound questions about the nature of causality. Spacetime contains light cones, which define which events can influence one another. Events inside your past light cone can affect you. Events inside your future light cone can be affected by you. Events outside both cones are disconnected. You cannot reach them, and they cannot reach you. This structure protects causality. No matter how you move, you cannot influence an event outside your light cone, because doing so would require faster-than-light travel, which is impossible. Time dilation and relativity do not allow paradoxes, because space-time geometry enforces causal order. Although the block universe interpretation fits naturally with relativity, physicists do not agree on whether it is the final word. Some argue that time is emergent, not fundamental, that it arises from entanglement patterns in quantum fields or from thermodynamic processes. Others propose that spacetime itself emerges from more primitive information structures. These ideas are active areas of research. None have been conclusively proven. They remain speculative, but they reflect an attempt to reconcile the smooth geometry of spacetime with the discrete, probabilistic nature of quantum mechanics. Even without speculation, the behavior of time in known physics is rich enough to challenge every intuition humans possess. Consider the twin paradox, possibly the most famous illustration of time dilation. One twin travels on a spaceship at near light speed, while the other remains on Earth. When the traveling twin returns, they are younger than their sibling. There is no contradiction because the twins follow different world lines with different proper times. Motion through spacetime determines aging. Life becomes path-dependent. Biological processes and personal identity become linked to geometry. What feels like a story about siblings becomes a demonstration of time's relativity. One of the strangest implications of time dilation is that for highly relativistic travelers, entire civilizations could rise and fall during what feels like a short trip. If you could travel close to the speed of light, a journey lasting a few years for you might span centuries or millennia in the rest of the universe. Time would pass differently along your world line. This does not violate physics. It is a direct consequence of relativity. The universe allows you to travel into the future, not by jumping through time, but by moving through spacetime in such a way that your aging slows compared to others. This is not time travel in the fictional sense. It is the natural behavior of time under relativity. Gravity produces equally dramatic examples of time warping in astrophysical settings. Neutron stars, with densities so high that a teaspoon of their matter outweighs mountains, slow time drastically. Clocks on their surfaces tick far slower than those far from their gravitational fields. This effect becomes even more extreme near black holes. At the event horizon, the stretching of time becomes infinite. Time inside the horizon cannot be compared meaningfully to time outside. For an external observer watching an object fall in, the object appears frozen at the horizon. For the falling object, time continues smoothly. These two descriptions coexist because space-time allows different observers to experience different geometries without contradiction. The warping of time also influences the structure of the universe itself. The expansion of space-time stretches not only distances, but also the relationship between moments. As the universe expands, cosmic time progresses, setting a universal measure for the evolution of large-scale structure. But local time always depends on gravity. The deeper a region lies in a gravitational well, the slower cosmic evolution appears to that region. This gradient of time shapes how galaxies cluster, how stars orbit within galaxies, and how black holes interact with their surroundings. In regions of extreme gravity, such as near-merging black holes, time becomes dynamic and chaotic. Gravitational waves produced during mergers compress and stretch space-time as they pass, altering the rate at which clocks tick. These distortions are incredibly small on Earth, but near the source they shape the evolution of matter and energy. Time is not a rigid parameter, but a variable woven into the universe's motion. Despite its strange behavior, time also exhibits deep consistency. All observers agree on the ordering of events connected by cause and effect. Proper time, the time experienced along a world line, is invariant. Even if observers disagree about simultaneity or the duration of processes, they agree on what happens to whom. This consistency preserves the structure of reality even as the experience of time remains flexible. Human perception, however, continues to anchor people to a comfortable illusion. You feel time pass uniformly because your brain generates a steady psychological rhythm. This rhythm has nothing to do with space-time. It is created by neural processes, biological cycles, and chemical changes. Your brain cannot detect time dilation or curvature because those effects are too small at human scales. You feel the continuity of moments not because time flows, but because your consciousness stitches together separate events into a narrative. The sensation of now is a construction, not a fundamental feature of physics. This does not diminish the reality of your experience. It simply means that your experience is one version of time among many possible versions defined by space-time. An observer in orbit experiences time differently. A particle moving near the speed of light experiences time differently. A clock near a black hole experiences time differently. The universe contains countless nows, all valid, none privileged. Reality is not a river flowing forward, but a four-dimensional structure in which observers trace paths determined by geometry. Time's behavior becomes even stranger when considering quantum mechanics. Quantum systems evolve according to probabilities and wave functions, which introduce uncertainty into the evolution of physical states. How this probabilistic evolution fits into the deterministic geometry of spacetime remains unknown. Some theories propose that time emerges from entanglement patterns among particles. Others suggest that time arises when quantum systems become classical. These ideas are still speculative, and no consensus exists. What is known is that relativity's time dilation remains intact across all observed regimes. As scientists probe deeper into time, they confront questions that border on philosophical. Does the universe have a preferred direction of time? Why does entropy increase? Why do we remember the past but not the future? Why does consciousness experience time as a flow? Some answers relate to thermodynamics. Entropy increases because higher entropy states are more probable. Others relate to initial conditions. The early universe began in a state of low entropy, setting a direction for time's arrow. But these explanations do not touch the emotional reality of time, the sense of loss, anticipation, and passage. Physics describes time's structure, but it does not yet explain its subjective experience. Despite the mysteries, one thing is clear: time is far more flexible than intuition suggests. It bends under gravity, slows with motion, stretches near black holes, diverges between observers, and defines the causal structure of the universe. It is not a universal metronome, but a malleable dimension bound to the fabric of space-time. The strangeness of time does not make reality chaotic or unintelligible. It reveals a deeper consistency, a geometry that governs all events. Once you understand that time is shaped by space-time, not separate from it, the universe becomes more coherent, not less. You see that your life is not a sequence of moments passing through a universal now, but a world line. Your unique path through the four-dimensional structure of reality. Space appears empty. When you look outward into the night, you see dark regions between stars, vast pockets of nothingness stretching across the universe. Even around you, the air seems like a negligible mixture of gases in an otherwise hollow container. But this impression is an illusion born from the limits of human senses. What feels like emptiness is not empty. Space is not a void waiting to be filled by matter. It is an active, dynamic structure with properties of its own, shaped by fields, curvature, and quantum fluctuations. It is the stage on which the universe unfolds, but it is also part of the play itself. When you begin to examine space carefully, you discover that it is not passive, but restless, filled with invisible architecture that determines the behavior of everything that exists. The first surprising truth is that space has geometry. Distances, angles, and volumes are not arbitrary. They are determined by the metric of spacetime, a mathematical description that tells you how to calculate separations between points. In everyday life, this geometry appears Euclidean. Triangles have angles summing to 180 degrees. Parallel lines never meet. Circles have predictable perimeters. But these rules hold only because spacetime is nearly flat at human scales. When you move to larger distances or stronger gravitational fields, Euclidean geometry begins to fail. Lines that appear straight may not be. Parallel paths can converge or diverge. The sum of angles in a triangle can be greater or less than 180 degrees. These deviations reveal that space is curved, even if the curvature is imperceptible to your senses. Curvature is not something imposed on space from outside. It is an intrinsic property, shaped by the presence of mass and energy. When spacetime curves, distances change, surfaces distort, and paths bend. Objects moving freely follow geodesics that reflect this geometry. Light follows these paths as well, which is why gravitational lensing occurs. Space bends around massive objects because spacetime itself is curved, not because the objects exert a force in the classical sense. Curvature becomes the blueprint for motion. Even in regions that appear empty of matter, space holds energy. Quantum field theory teaches that every type of particle is accompanied by a field that fills all of spacetime. These fields are not static. They fluctuate constantly, producing temporary particle-antiparticle pairs that appear and vanish too quickly to observe directly. These quantum fluctuations are not theoretical artifacts. They have measurable consequences. They produce the Casimir effect, where two uncharged metal plates placed close together experience a force due to differences in vacuum fluctuations. They shift energy levels in atoms, contributing to the Lamb shift. They allow Hawking radiation around black holes. These are not signs of emptiness, but signs of a seething quantum activity embedded in the fabric of space. Space also holds vacuum energy, an energy that remains even when all matter and radiation are removed. The value of this energy determines how the universe expands. If vacuum energy was zero, the universe's expansion would behave differently. If vacuum energy were much larger, galaxies could never form. The tiny but non-zero vacuum energy observed today drives the accelerated expansion of the universe, acting as what scientists call dark energy. This suggests that space not only contains energy, but contributes to cosmic evolution in profound ways. Another surprising truth is that space can expand. This expansion is not motion through a pre-existing container, but a stretching of the metric itself. As the universe expands, galaxies move farther apart, not because they travel through space, but because the distance between them increases. Light traveling across the universe is stretched by expansion, increasing its wavelength. This stretching is measurable in the redshift of distant galaxies. When you observe a galaxy billions of light years away, you are not merely seeing an object far away. You are seeing an object in a region of space that has expanded dramatically since the light left it. The redness of the light is a record of how much space has stretched. This expansion leads to another important insight. Space cannot be thought of as a container with fixed size or volume. Instead, volume itself is dynamic, determined by spacetime's geometry. The universe has no edge because the expansion occurs everywhere. You cannot travel to the boundary of the universe because there is no boundary. The idea of an outside is meaningless. Space is self-contained. It grows not into something but from itself. This challenges intuition in profound ways. People imagine expansion as an explosion, but it is not. It is a geometric change, not a kinetic one. Space also has dimensionality. At macroscopic scales, it appears three-dimensional, with length, width, and height. But at quantum scales, the structure of space may not be smooth. Some theories propose that space-time becomes foamy at the Planck length, with fluctuations in geometry so extreme that the concept of distance breaks down. These ideas remain speculative and unconfirmed, but they reflect an attempt to reconcile general relativity with quantum mechanics. Whether space-time remains smooth all the way down or becomes granular is one of the greatest open questions in physics. Even at large scales, space reveals structure. Galaxies cluster into filaments and walls, separated by vast cosmic voids. These patterns form a cosmic web, shaped by gravity, acting on dark matter, and influenced by the expansion of space. The distribution of matter reflects the geometry of space-time and also reshapes that geometry in return. Space is not uniform, it is sculpted by the mass within it. Dense regions pull matter inward. Empty regions expand more quickly. Over billions of years, these interactions produce the intricate patterns we see in the large-scale structure of the universe. One of the most mysterious aspects of space is that its geometry affects quantum fields and quantum fields affect its geometry. This interplay becomes significant near black holes, where extreme curvature interacts with high-energy quantum processes. Hawking radiation arises because quantum fields in curved spacetime behave differently near horizons. The vacuum is not stable in these regions, producing a flow of particles outward. This evaporation of black holes suggests that spacetime and quantum fields are deeply connected. But the exact nature of this connection is unknown. General relativity treats spacetime as smooth, while quantum mechanics demands granularity and uncertainty. Reconciling the two remains perhaps the deepest challenge in physics. Another peculiar property of space is that it determines what it means to move. Motion is not defined relative to a fixed background. Instead, it is defined by changing coordinates within spacetime. You cannot ask how fast you're moving through space. You can only ask relative to what. Motion is relational, not absolute. Even the speed of light, normally thought of as constant, can be seen as a property of spacetime. Light moves at the maximum speed allowed by the structure of spacetime. That speed is not imposed externally. It is built into the geometry. Space also interacts with energy in subtle ways. The concept of gravitational potential arises from geometry. A region with a gravitational well has a different metric than a region without one. This affects how particles move and how clocks tick. The familiar idea of being higher or lower in a gravitational field corresponds to being in regions of different spacetime curvature. These differences influence everything from orbital motion to the behavior of atoms. Even the energy levels of electrons in atoms are slightly shifted by gravity, though this shift is so small that it requires extremely precise instruments to detect. Despite its complexity, space remains invisible. You cannot see curvature directly. You cannot sense quantum fluctuations. You cannot perceive expansion without studying light from distant galaxies. Human senses evolved to navigate a narrow set of conditions, not to detect the fabric of the cosmos. It is only through mathematics, measurement, and theory that the true nature of space becomes visible. Yet once you understand what space really is, its apparent emptiness becomes even more astonishing. You begin to see it as an active participant in the universe. It shapes motion, determines the speed of light, influences the passage of time, supports quantum fields, and drives cosmic expansion. Space is not a backdrop. It is a dynamic, evolving, energetic fabric that permeates everything. Even the idea of empty space is more complicated than it appears. The vacuum is filled with quantum fluctuations, virtual particles, and fields that permeate every region of space-time. These fields can never truly reach zero. They always retain a minimum energy determined by quantum uncertainty. This means that even the most perfect vacuum still contains energy, momentum, and structure. The emptiness of space is an illusion created by the absence of matter, not by the absence of activity. This vacuum structure leads to important consequences. For example, the vacuum state of a quantum field depends on the curvature of space-time. A vacuum defined in flat space is different from a vacuum defined near a black hole or in an expanding universe. This difference influences particle creation, energy distribution, and even the thermodynamics of space-time. It suggests that space and matter are inseparable at the fundamental level. They co-create the structure of reality. Another subtle feature of space is that it resists compression. You cannot squeeze space to arbitrarily small sizes without encountering quantum effects that push back. This resistance may help explain why the early universe expanded so rapidly during inflation. Vacuum energy dominated during that period, driving exponential expansion. When inflation ended, the vacuum energy decayed into matter and radiation, shaping the universe we see today. The fact that vacuum energy can influence the expansion rate of the entire cosmos highlights how deeply space is woven into the fabric of physics. Perhaps the most profound realization is that space does not exist independently of time. Without time, distances have no meaning. Without space, durations have no context. They form a single structure, space-time, and everything that happens occurs within that structure. When you move, you shift your direction in space-time. When time dilates, your world line bends. When gravity acts, space-time curves. When space expands, time evolves. These are not separate behaviors, but different aspects of one geometric entity. Understanding space as something dynamic, structured, and energetic changes the way you see the universe. You begin to recognize that what appears empty is actually full. What appears still is constantly fluctuating. What appears rigid is flexible. What appears simple is profoundly complex. Space is the silent stage on which the cosmic drama unfolds, but it is also the scriptwriter, the director, and sometimes even the actor. It determines how the actors move, how scenes transition, and how the entire story of the universe evolves. Space shapes the universe, but it is also shaped by the universe. Curvature arises from energy. Geometry evolves with time. Fields fill every region. Light travels along geodesics carved by mass. Particles emerge from fluctuations in the vacuum. Galaxies form as matter collapses under gravity. Stars ignite as gas clouds condense. Life appears in regions where space-time supports stable structures. In seeing space clearly, you begin to understand that the universe is not made primarily of matter. It is made of space-time itself. Matter simply rides atop this structure, responding to its curvature, influencing its shape, and participating in its evolution. Space is not the absence of things, it is the presence of a profound and intricate structure that underlies everything. In the quiet regions of the universe, space-time behaves gently. Distances stretch smoothly, time passes predictably, and curvature is so slight that only sensitive instruments can detect it. But not all regions of the cosmos are gentle. Some places push space-time to its limits, revealing what happens when gravity becomes overwhelming, when density skyrockets, when rotation twists geometry into knots, and when light itself becomes trapped by curvature. These places, black holes, neutron stars, ultra-dense remnants of supernova, show that space-time is not merely a flexible fabric, but a dynamic, reactive entity capable of extreme contortions. By studying these environments, physicists glimpse not only the power of general relativity, but also the boundaries where our current understanding might break. The simplest extreme object predicted by Einstein's equations is the Schwarzschild black hole. It forms when a massive star collapses under its own gravity, crushing matter into a point, an infinitely dense singularity surrounded by an event horizon. At the horizon, the curvature of spacetime becomes so steep that all possible paths forward lead inward. No matter which direction you try to escape, your future points toward the center. This is not a force pulling you in, but a geometric inevitability. Inside the horizon, space and time exchange roles. Moving outward becomes as impossible as moving backward in time. Crossing the horizon does not feel dramatic to the falling observer. No sudden tearing, no wall of fire. But the outside universe sees you freeze in time, fading slowly as your light becomes redder, stretched by the intense gravitational field. The region outside a Schwarzschild black hole contains several interesting structures. One of them is the photon sphere, a spherical shell at which light can orbit the black hole indefinitely. This orbit is unstable. The slightest disturbance sends the photon inward toward the horizon or outward into space. But its existence reveals something profound. Space-time curvature near a black hole is strong enough to create circular paths for light itself. No mirror or material boundary is needed. Geometry alone provides the path. This photon sphere contributes to the famous shadow seen in black hole images. Photons skimming this region either circle multiple times before escaping or fall inward, creating a dark central void surrounded by a bright ring. Even before matter crosses the horizon, tidal forces can be enormous. Near Earth, tides gently stretch and compress bodies because the gravitational field changes slightly from your head to your feet. Near a black hole, especially a stellar mass one, the gradient becomes so extreme that it can pull atoms apart. This effect, often called spaghettification, stretches objects into long, thin strands. But tidal forces depend on the black hole's mass. Paradoxically, supermassive black holes produce gentler tides at the horizon because their curvature changes more gradually. A person falling into a supermassive black hole would cross the horizon without immediate destruction, only encountering lethal forces much deeper inside. Rotation complicates this picture dramatically. Most black holes spin, and when they do, space-time cannot remain still around them. A rotating black hole drags space-time along with it, twisting the geometry in a process known as frame dragging. Near such a black hole, sitting still relative to the distant universe becomes impossible. The fabric of space-time moves and you're carried with it. This region, called the ergosphere, lies outside the event horizon and has a curious property. Every object within it must rotate in the same direction as the black hole, even if it tries to resist. The ergosphere is not a solid object, but a region where space-time is pulled so strongly that its geometry forbids stationary motion. Inside this region, new possibilities emerge. Because the dragging of space-time adds energy to particles, it becomes theoretically possible to extract rotational energy from the black hole. This idea, proposed by Roger Penrose, involves a particle entering the ergosphere, splitting and sending one fragment into the horizon, while the other escapes with more energy than it had originally. This process has not yet been directly observed, but many astrophysicists believe it may help power some of the universe's brightest phenomena, including relativistic jets, streams of plasma propelled at near-light speed from the regions around supermassive black holes. The geometry of a rotating black hole, described by the Kerr solution, is more complex than the Schwarzschild case. Instead of a point singularity, the Kerr metric predicts a ring singularity. This ring has theoretical implications, some of which remain controversial. Mathematical extensions of the Kerr solution suggest the possibility of wormholes or paths to other regions of spacetime. However, these features depend on idealized assumptions. No rotation limits, no perturbations, no quantum effects. Real black holes formed from collapsing stars and surrounded by chaotic environments likely do not resemble these perfect geometries. Still, the Kerr solution shows that space-time can structure itself in ways far beyond everyday intuition. The behavior of space-time near compact objects becomes even more fascinating when considering neutron stars. These remnants of supernova explosions pack more mass than the Sun into a sphere about 20 kilometers wide. A teaspoon of neutron star material would weigh billions of tons on Earth. In these environments, atomic nuclei are crushed together, electrons merge with protons to form neutrons, and the resulting matter becomes so dense that it resembles a giant atomic nucleus. The curvature around a neutron star is immense. Time slows significantly. Light bends noticeably. A clock on its surface would tick far slower than a distant clock. The surface gravity is so extreme that even small irregularities could trigger starquakes, sudden shifts in the crust that send ripples through space-time. Neutron stars often spin rapidly, some completing hundreds of rotations per second. These pulsars send beams of radiation sweeping across space, like cosmic lighthouses. The regularity of their pulses makes them excellent probes of space-time. When two neutron stars orbit each other, their motion gradually decays as they emit gravitational waves. Decades before such waves were detected directly, scientists measured this orbital decay precisely and found it matched Einstein's predictions. The energy lost matched the gravitational radiation predicted by general relativity. This was one of the earliest confirmations of spacetime's ability to radiate energy. Binary neutron star mergers provide one of the richest laboratories for studying spacetime. When two neutron stars spiral toward each other, their intense gravitational fields distort each other's shapes. Their motion produces gravitational waves that ripple outward through spacetime. When they finally collide, the resulting explosion creates heavy elements such as gold and platinum. These mergers produce both gravitational and electromagnetic signals, allowing scientists to test general relativity from multiple perspectives. The 2017 detection of such a merger confirmed not only the existence of gravitational waves, but also their speed, waveform, and polarization. Everything matched Einstein's predictions. Despite these successes, extreme environments also reveal limitations in our understanding. Singularities predicted by general relativity represent points where curvature becomes infinite. But infinities in physics usually signal that the theory has been pushed beyond its domain of validity. Quantum mechanics must play a role in these regimes, but general relativity cannot incorporate it. The interior of a black hole, where spacetime collapses into a singularity, remains a mystery. The laws of physics, as currently understood, cannot describe what happens there. Some theories propose that quantum effects might smear out the singularity or replace it with a more complex structure. Others suggest that spacetime itself may dissolve into something more fundamental, but none of these ideas have been confirmed. Frame dragging near rotating black holes and neutron stars shows that spacetime can behave like a fluid, twisting in response to motion. This invites comparisons to superfluidity or other condensed matter phenomena, though such analogies are imperfect. Nonetheless, they highlight the dynamic nature of spacetime and hint at deeper structural similarities between gravity and quantum mechanics. The precise relationship remains unknown. Another peculiar feature of extreme spacetime is gravitational redshift. Light climbing out of a strong gravitational field loses energy and shifts to longer wavelengths. Near a black hole, this shift becomes so large that light emitted close to the horizon may never reach a distant observer. This is not because the light slows, it always travels at the speed of light locally. Instead, spacetime curvature lengthens its wavelength until it becomes undetectable. From afar, the region near the horizon looks dimmer, not because it lacks activity, but because time dilation suppresses the flow of information from that region. When matter falls into a black hole, it forms an accretion disk. The motion within this disk is governed by a combination of turbulence, magnetic fields, and extreme relativistic effects. Particles in the inner disk move so fast that their orbital velocity approaches the speed of light. Time dilation alters the observed brightness. Doppler boosting enhances the light from the portions moving toward us and dims the opposite side. All of these effects contribute to the asymmetric ring seen in black hole images. The bright crescent is not simply a feature of the disk, but a result of spacetime shaping the direction and intensity of light. Extreme spacetime also influences particle physics. Near a black hole, quantum fluctuations interact with the curved geometry to produce Hawking radiation, a faint emission that causes black holes to lose mass over time. Although Hawking radiation has not been observed directly, it remains one of the clearest insights into how quantum fields behave in curved spacetime. It shows that horizons are not perfectly stable boundaries, but active interfaces where quantum processes take place. If Hawking radiation is real, it implies that black holes eventually evaporate completely. But what remains afterward is unknown. Does the information contained in the black hole disappear? Is it preserved in a transformed state? This information paradox remains one of the deepest puzzles in modern physics and highlights the need for a unified theory of quantum gravity. In regions of extreme curvature, spacetime becomes not merely a container, but a participant in physical interactions. It stretches, twists, vibrates, and influences the behavior of particles and fields. Yet despite its complexity, general relativity continues to describe these environments with remarkable accuracy. Observations of neutron star motion, black hole mergers, frame-dragging signatures, gravitational redshift, and accretion disk dynamics all confirm the predictions of Einstein's equations. Still, the extreme universe pushes the theory to its limits. Singularities remain unresolved. The interaction between quantum fields and curved spacetime hints at deeper laws. The behavior of spacetime at the Planck scale, where curvature and quantum fluctuations become comparable, is unknown. These mysteries suggest that general relativity, though powerful, is only an approximation of a deeper theory. The existence of extreme spacetime environments does not contradict the elegance of general relativity. Instead, it reveals the theory's strength. Einstein's equations remain consistent even in conditions far removed from everyday experience. They describe the cosmos not as a gentle landscape, but as a dynamic arena capable of extraordinary phenomena. Understanding these regions provides insight into the universe's most dramatic events and into the fundamental nature of space and time themselves. For all its beauty, accuracy, and predictive power, general relativity carries within it a quiet tension, a tension so fundamental that it signals the theory's incompleteness. Einstein's description of spacetime geometry remains the most accurate account of gravity ever created, matching every experiment across solar system scales, astrophysical scales, and cosmological scales. Yet whenever scientists push the theory into domains where gravity becomes extremely strong or extremely small, the framework begins to tear. Curvature grows without bound, predictions diverge, singularities appear, quantum effects refuse to be ignored. The smooth fabric of spacetime, which behaves so elegantly across the cosmos, begins to fray at the edges. These failures are not signs that general relativity is wrong. They are signs that it is only part of a deeper story. The most obvious indication of incompleteness appears at singularities, places where density, curvature, and tidal forces become infinite. According to general relativity, the center of every black hole contains such a singularity. The Big Bang itself is described as a singularity, a point where space-time begins. But infinities in physics are warnings, not destinations. They signal that a theory has been pushed beyond its domain of validity. Singularities are not physical objects. They are breakdowns in the mathematical structure of general relativity. They tell us the theory cannot describe what happens inside the event horizon or at the beginning of the universe. Something deeper must exist beyond classical spacetime geometry. Quantum mechanics provides another point of conflict. At small scales, the universe behaves in ways that general relativity cannot accommodate. Particles exist in superpositions, fields fluctuate unpredictably, energy levels become quantized. Quantum uncertainty forbids precise knowledge of both position and momentum. But general relativity describes spacetime as smooth and continuous, defined by precise geometrical relationships. Trying to merge the two frameworks leads to contradictions. Curvature becomes undefined when quantum fluctuations disrupt the notion of a smooth metric. Vacuum energy, predicted by quantum field theory, gives rise to a cosmological constant so large that it would crush the universe, a mismatch between theory and observation so extreme that it remains one of the most pressing problems in physics. Even the concept of a point particle becomes problematic when gravity is considered. Quantum particles occupy regions of space, not fixed points, but a particle with mass curves spacetime. If you try to compress that mass into a smaller region, the curvature becomes stronger. If the region becomes too small, the equations predict a black hole. This implies a minimum length scale where the classical description breaks down, the Planck length. At this scale, spacetime itself becomes subject to quantum uncertainty. Geometry fluctuates, distances lose meaning. The smoothness of spacetime dissolves into something granular or probabilistic. General relativity cannot accommodate such behavior, but ignoring it contradicts quantum principles. Another conflict arises when trying to combine the principles of superposition with spacetime geometry. In quantum mechanics, a particle can exist in multiple states at once. But if mass curves spacetime, then a particle in a superposition of positions should create a superposition of geometries. General relativity does not allow spacetime to exist in two shapes simultaneously. The theory demands a single, definite geometry. This contradiction indicates that a quantum theory of gravity must be capable of describing superpositions of spacetimes, something no classical framework can do. The information paradox provides yet another sign of incompleteness. When matter falls into a black hole, it carries information about its quantum state. But according to classical general relativity, anything entering a black hole is lost forever, disappearing behind the horizon until it reaches the singularity. Hawking's prediction of black hole evaporation complicates this further. If black holes emit radiation, eventually evaporate, and disappear completely, where does the information go? If it is destroyed, quantum mechanics is violated because quantum evolution must preserve information. If it escapes somehow, general relativity must be modified to allow information to leave or remain encoded in the radiation. Neither answer fits cleanly within current frameworks. This paradox reveals that general relativity and quantum mechanics cannot simply coexist without modification. They must be unified. Even observations of the universe's expansion hint at deeper physics. When scientists discovered that the expansion was accelerating, they used Einstein's equations to model the phenomenon and concluded that some form of dark energy must exist. But the nature of dark energy is unknown. It behaves like vacuum energy, yet quantum field theory predicts a value vastly different from what is observed. The discrepancy, by some estimates a factor of 10 or 120, remains one of the greatest unsolved problems in physics. This mismatch suggests that the way general relativity handles vacuum energy is incomplete. General relativity also struggles at the interface between strong gravity and quantum phenomena, such as in the cores of neutron stars. While observations of neutron star behavior match relativity at large scales, the extreme densities inside these objects push the theory into regimes where quantum forces and gravity both become dominant. The equations become unstable. Quantum chromodynamics and general relativity must both be applied, but they do not merge smoothly. Simulations break down. Predictions diverge. These issues show that the theory lacks the tools needed to describe matter under extreme conditions. Another clue comes from the study of inflation, the rapid expansion of the early universe. Inflation explains the large-scale uniformity of the cosmos, the distribution of galaxies, and the temperature patterns in the cosmic microwave background. But inflation requires quantum fields operating in a regime where gravitational effects are enormous. The mathematics used to model inflation combines general relativity with quantum field theory in a semi-classical approximation. This works surprisingly well, but it is not exact. A true quantum theory of spacetime is needed to understand the beginning of inflation, or what came before it. Without such a theory, the earliest moments of the universe remain hidden behind mathematical approximations. The quest for quantum gravity, an attempt to unify general relativity with quantum mechanics, has produced several competing approaches. One of the most prominent is string theory, which proposes that particles are not point-like, but rather one-dimensional strings, whose vibrations give rise to different types of matter and forces. In this framework, spacetime emerges from deeper structures, and gravity arises naturally as one of the vibrational modes. String theory allows for spacetime curvature and quantum behavior to coexist, but it requires extra dimensions and mathematical structures not yet supported by direct evidence. Although it offers a compelling mathematical framework, it remains a theoretical construct awaiting empirical validation. Another major approach is loop quantum gravity, which attempts to quantize spacetime itself. Instead of treating spacetime as smooth, it models it as a network of discrete loops. Distances, areas, and volumes become quantized. Geometry arises from the connections between these loops. In this view, spacetime has a granular structure at the Planck scale. Singularities do not form because spacetime cannot be compressed beyond a minimum size. Loop quantum gravity does not require extra dimensions, but it also remains incomplete, lacking a clear way to incorporate matter fields and recover known physics in all regimes. Other proposals exist as well, including causal dynamical triangulations, emergent spacetime theories, the ADS-CFT correspondence, and the holographic principle. The holographic principle in particular suggests a radical idea that the three-dimensional world we experience may arise from information encoded on a lower dimensional boundary. This idea, supported by string theory and black hole thermodynamics, implies that spacetime itself may be emergent rather than fundamental. If spacetime arises from quantum information, then geometry becomes a derived concept, not a basic ingredient of reality. Despite the promise of these approaches, none has produced a complete, experimentally verified theory of quantum gravity. The difficulty lies in the fact that quantum gravitational effects become significant only at the Planck scale, energies far beyond the reach of current experiments. Cosmological observations, black hole physics, and particle accelerators provide indirect clues, but none can probe the required regime directly. The universe hides its deepest secrets behind inaccessible scales. Even though general relativity fails in these extreme conditions, its failures are remarkably structured. They highlight exactly where a deeper theory is needed: at singularities, at the Planck scale, in strong gravitational fields interacting with quantum processes, and in the earliest moments of the universe. These failures point toward a unification of geometry and quantum information, suggesting that spacetime may not be a fundamental entity, but an emergent phenomenon built from something else. Whether That something is strings, loops, networks, entanglement patterns, or a yet undiscovered framework remains the greatest open question in theoretical physics. General relativity remains one of the most successful theories ever created, but it is not the final story. It describes the large-scale universe with unmatched precision, but it cannot describe the small-scale quantum world. It explains black hole geometry, but cannot explain what happens at the singularity. It models gravitational waves, but not their quantum nature. It describes the expansion of the universe, but not the origin of dark energy. Every success brings clarity, and every breakdown points toward the next revolution. The incompleteness of general relativity is not a weakness. It is a sign of the theory's strength. A great theory answers many questions but leaves deeper ones behind. Einstein's theory reshaped our understanding of reality, but it also revealed mysteries that extend far beyond its reach. These mysteries, singularities, quantum spacetime, the information paradox, the nature of the vacuum, the unification of forces, serve as the guideposts for future discoveries. Humanity now stands where Einstein once stood, on the edge of the known, staring into an unknown that demands new ideas, new mathematics, and new perspectives. Just as Newton's framework gave way to Einstein's framework will someday give way to a deeper theory. It will explain where spacetime comes from, how geometry emerges, how gravity behaves at quantum scales, and what truly lies at the heart of a black hole, or at the beginning of time itself. General relativity is the greatest geometric description of the universe ever written. But the universe is not finished telling its story, and neither is the physics that seeks to understand it. For something that feels so distant from daily experience, spacetime shapes almost every aspect of modern life. People walk through their routines as if space is empty and time is constant, unaware that their phones, cars, communication systems, satellites, power grids, and global economy all depend on the subtle curvature of spacetime and the relativity of motion. Without Einstein's insights, much of the technology that defines the 21st century would malfunction or collapse entirely. What seems abstract and cosmic is, in reality, woven into the infrastructure of ordinary existence. Every time someone uses GPS, they are relying on the geometry of spacetime. Satellites orbit Earth high above the surface, where gravity is weaker and time runs faster. Their motion also slows their clocks due to special relativity. These two effects do not cancel. They combine in a precise way that makes the satellite clocks tick about 38 microseconds faster per day compared to clocks on Earth. That difference seems tiny, but if uncorrected, GPS errors would accumulate at a rate of roughly 10 kilometers per day, making the system useless. Engineers must continuously adjust for Earth's curvature of spacetime to ensure that your location appears correctly on your screen. Navigation apps, aviation systems, cargo shipping routes, emergency services, and financial logistics all rely on these corrections. The invisible machinery of modern civilization would fail without relativistic timekeeping. Even communication networks feel the influence of spacetime. Signals traveling through optical fibers, bouncing off satellites, or transferring between antennas must obey the finite speed of light. Small timing differences accumulate across global networks. Financial markets depend on timestamp accuracy to regulate high-speed trading. Scientific experiments require nanosecond precision to compare measurements taken on opposite sides of the planet. All these systems assume that the geometry of spacetime is known, stable, and predictable. Without relativity, the global network would fall out of sync. The same is true for technologies used in research. Particle accelerators, such as the Large Hadron Collider, rely on relativity to predict how particles behave at near-light speeds. Without special relativity, the design of these machines would be impossible. As particles accelerate and gain energy, their mass increases according to relativistic dynamics. Engineers must use Einstein's equations to determine how much magnetic field strength is required to bend their paths. Detectors must be calibrated using relativistic corrections to interpret the resulting collisions accurately. Even the discovery of the Higgs boson depended on a deep understanding of how particles move through spacetime. Astronomy provides another striking example of relativity in action. Telescopes do more than capture light. They interpret signals distorted by spacetime. Astronomers must correct for gravitational lensing, a curvature effect that bends the path of light from distant galaxies. They must adjust for gravitational redshift when studying stars near compact objects. They must compensate for Earth's motion through spacetime, which introduces Doppler shifts into observations. Without accounting for these factors, data would be scrambled and distances miscalculated. When astronomers map cosmic structures or measure the expansion of the universe, they are reading the geometry of spacetime written in light. Even the stability of satellites depends on general relativity. Orbital motion is governed not by Newton's gravity, but by geodesics in curved spacetime. Satellites drift unless their orbits account for Earth's shape, its rotation, the oblateness of its mass distribution, and the relativistic corrections to gravitational potential. Engineers must also consider frame dragging, Earth's rotation, slightly twisting spacetime, which subtly influences satellite paths. These effects are small, but over time they accumulate. Spacecraft navigation depends on precise modeling of spacetime curvature. Sending a probe to Mars or beyond requires accounting for how gravitational wells alter the trajectory. Even slight errors can cause missions to miss their targets by millions of kilometers. Relativity also shapes the atomic clocks used worldwide. These clocks do not simply count oscillations, they measure the frequency of quantum transitions in atoms. But gravity alters this frequency. Clocks on mountains tick faster than those at sea level. Clocks on airplanes tick differently than those on the ground. Laboratories conducting high-precision experiments must measure and compensate for these variations. Some of the newest optical clocks are so sensitive that lifting them by a centimeter changes their tick rate enough to detect. These clocks allow scientists to measure gravitational potential differences across small distances, essentially using time itself as a probe for curvature. Technology now allows humans to feel the shape of spacetime through the ticking of a clock. Relativity even influences the electricity flowing through your home. The synchronization of power grids across continents requires precise timekeeping. If time did not behave consistently in different regions due to gravity or motion, electrical networks would drift out of phase, causing instability or outages. Engineers rely on relativistic corrections in timing signals transmitted through fiber optic lines and GPS receivers. Even small mismatches can lead to significant problems. Thus, the stability of the modern power grid depends on an understanding of spacetime. In medical technology, relativity plays a subtler role. Positron emission tomography, PET scans, MRI machines, and radiation therapies depend on precise knowledge of particle behavior, energy levels, and electromagnetic interactions, all rooted in relativistic quantum mechanics. The lifetime of particles used in these machines is influenced by time dilation. Designing equipment that accounts for these effects ensures accurate imaging and safe treatment. Even technologies that seem purely biological, like high-resolution microscopes, rely indirectly on principles derived from relativity. Another example arises in computer engineering. Modern processors operate at frequencies so high and at scales so small that signal delays, limited by the speed of light, must be accounted for in circuit design. The layout of chips, the placement of components, and the architecture of data pathways reflect an understanding that nothing, not even information, inside a processor can outrun the constraints of spacetime. Engineers now design hardware with geometry in mind. Even though these effects are classical in most cases, they arise because relativistic principles constrain the ultimate limits of communication speed. Climate science also depends on relativistic physics. Satellites used to monitor weather patterns, sea levels, atmospheric composition, and global temperatures must incorporate general relativity to stay synchronized with ground-based sensors. The accuracy of climate models relies on data gathered through instruments that function correctly only when spacetime curvature is accounted for. Without relativistic navigation and timing, large-scale climate observations would become unreliable, undermining predictions essential for agriculture, infrastructure, and disaster preparedness. Geological surveys rely on relativity as well. Satellites used for mapping Earth's gravitational field detect tiny variations in gravitational potential that indicate the presence of underground structures, tectonic stresses, or changes in water distribution. These satellites depend on precise timing and positioning provided by relativistic corrections. Their data help predict earthquakes, monitor volcanic activity, and manage natural resources. Once again, spacetime curvature becomes a tool for understanding and protecting life on Earth. Relativity's role extends to astrophysics in more dramatic ways. Observatories studying black holes, neutron stars, and gravitational waves rely on spacetime curvature as both a subject of study and a measurement tool. When LIGO detects gravitational waves, it measures distortions in spacetime smaller than a proton's width. These distortions alter the lengths of laser paths inside kilometers-long tunnels. Interpreting the signal requires understanding how spacetime vibrates. The success of these detections depends entirely on Einstein's equations. The Event Horizon Telescope, which produced the first image of a black hole's shadow, relies on relativity at every step. Light near the black hole is bent, delayed, redshifted, or trapped by spacetime curvature. To reconstruct an image, scientists must model these distortions precisely. The result is a picture, not of a physical object, but of spacetime geometry shaping the flow of light. Without relativity, such images would be meaningless. Even the study of the universe's origin and evolution depends on relativity. Cosmology, the science of the universe as a whole, relies on the Friedmann equations, derived from general relativity, to explain expansion, structure formation, cosmic microwave background radiation, and the growth of galaxies. Dark energy, dark matter, inflation, cosmic acceleration. These are not abstract ideas, but consequences of how spacetime behaves. Every cosmological model used today is rooted in the geometry of the universe described by Einstein. Yet even everyday experiences are touched indirectly by relativistic ideas. The fact that matter holds together, that atoms have stable energy levels, that chemical bonds form, all of these depend on relativistic quantum mechanics. Without relativity, gold would not have its distinctive color, mercury would not be liquid at room temperature, and the periodic table would look radically different. The world around you is shaped by relativistic effects, even in objects you handle without thought. In transportation, relativity affects the precision of inertial navigation systems used in aircraft, submarines, spacecraft, and autonomous vehicles. These systems integrate accelerations over time to determine position. If time does not behave predictably, these calculations break down. Engineers must therefore incorporate relativistic models into the design of guidance systems. Without them, long-distance travel and autonomous navigation would be unreliable. Emerging technologies continue to expand relativity's influence. Quantum communication networks, which rely on entanglement, are sensitive to spacetime curvature. Space-based quantum experiments test how entangled states respond to gravitational potential differences. Time-sensitive networks for autonomous vehicles, drones, and robotic systems depend on ever more precise synchronization tied to relativistic timekeeping. Even the next generation of internet protocols aims to incorporate relativistic constraints to ensure global consistency. As humanity prepares for deeper space exploration, relativity becomes even more essential. Missions to Mars, the outer planets, or beyond must account for how space-time affects signals, navigation, and spacecraft trajectories. A spacecraft traveling at high velocity experiences time differently from mission control on Earth. This influences life support planning, communication windows, and mission timing. Without relativity, long-duration missions could drift dangerously off course. Ultimately, space-time is not an abstract mathematical curiosity confined to physics research. It is the quiet engine behind the modern world. Its curvature guides the technology people use every day. Its structure shapes the tools we rely on. Its distortions create opportunities for discovery. The phones in our pockets, the machines in our hospitals, the satellites above our planet, and the telescopes scanning distant galaxies all depend on an understanding of spacetime's geometry. Relativity did not merely change physics, it changed civilization. It turned time into a tool, space into a measurable structure, and gravity into a predictable influence. It transformed navigation, communication, astronomy, engineering, and computation. As future technologies grow more precise, the influence of spacetime will deepen. Humans will build clocks that measure curvature within a room, detectors that observe quantum fluctuations in gravity, telescopes that map spacetime near black holes in real time, and spacecraft that navigate the solar system using relativistic frameworks. Spacetime surrounds every person. It shapes every motion. It touches every machine. It guides the evolution of the universe and the stability of daily life. Once you understand that relativity is hidden inside every moment of modern experience, you see the world differently. You begin to notice how deeply the cosmos is woven into ordinary existence, how the arc of a satellite, the ticking of a clock, and the path of a photon all whisper the same message. The fabric of space-time is the foundation of reality, and humanity has learned to use it. Space-time does not behave uniformly across the universe. Its curvature, geometry, and dynamics depend entirely on scale. At human scales, the curvature of Earth is detectable only through instruments, and time dilation is so small that people can live their entire lives without feeling it. But when you zoom out to planetary scales, orbital motion becomes a ballet choreographed by spacetime. Move farther still, to stars, galaxies, and clusters, and spacetime reveals deeper, more complex behavior. Across these vast ranges of size and mass, the rules remain the same, but their consequences change dramatically. Gravity becomes stronger or weaker, time stretches or compresses, and the behavior of matter reflects the curvature in ways that cannot be understood without embracing the geometry of spacetime. Each scale brings its own story, its own version of relativity, its own reflection of the universe's structure. At the scale of Earth, spacetime curvature is gentle but essential. The planet's mass creates a gravitational well that shapes the paths of falling objects, satellite orbits, ocean tides, and even the flow of time. The curvature here is weak enough that Newton's laws provide excellent approximations for many everyday phenomena. But relativity appears whenever precision matters. Clocks at the top of a skyscraper run faster than those at street level. GPS satellites must adjust their timing by microseconds to stay accurate. Even the physics of mountain formation depends on how Earth's mass distributes itself within its geometry. The planet's rotation also distorts spacetime slightly, producing frame-dragging effects so small that only refined measurements, like those from Gravity Probe B, can detect them. Yet these effects exist, quietly influencing motion around Earth. At this scale, spacetime feels familiar, but only because humans evolved within its mild curvature. Moving up to the scale of the solar system, the influence of spacetime becomes more dramatic. The Sun, containing nearly all the mass of the system, creates a deep gravitational well that governs planetary motion. Planets follow elliptical orbits, not because an invisible force pulls them, but because they move along geodesics shaped by the Sun's curvature. Mercury, closest to the Sun, travels through spacetime where curvature is strongest, leading to a precession that Newtonian physics could not explain. General relativity predicted this behavior perfectly. Light grazing the Sun curves slightly, a fact verified during eclipses and through modern instruments. Time passes slower near the Sun, and an observer hovering close to it would age more slowly than someone far away. Even the solar wind, a stream of charged particles, follows trajectories influenced by the curvature around the Sun. Comets with long orbits trace vast spiderweb-like paths through space-time, returning after decades or centuries to complete their journeys. Everything in the solar system moves according to geometry. As we expand to stellar scales, space-time becomes even more varied. Stars are scattered across the galaxy, each carving its own small well into the larger curvature of the Milky Way. Massive stars bend space-time more strongly than smaller ones, altering the orbits of nearby planets, debris fields, and binary companions. When stars cluster, their combined curvature creates complicated gravitational environments where motions intertwine. Star clusters form dense regions where space-time wells overlap. The behavior of stars in these clusters reveals the structure of space-time in areas where many masses interact. Their paths show the cumulative effects of curvature, producing chaotic motion or stable resonances depending on the configuration. These environments highlight how general relativity can create both order and chaos depending on mass distribution and energy. If you consider the life cycles of stars, spacetime takes on an even more dramatic role. When stars ignite, they resist gravitational collapse by producing pressure from nuclear fusion. When they die, they leave behind remnants, white dwarfs, neutron stars, or black holes, each representing spacetime under increasing stress. White dwarfs create modest curvature. Neutron stars produce curvature so intense that time dilation becomes significant, and black holes warp spacetime to its breaking point. Each type of remnant shows a different facet of spacetime geometry, as if layers of a deeper structure were being peeled back one by one. Neutron stars, for example, cause nearby objects to orbit with speeds unimaginable around normal stars. Their gravitational wells are so steep that light emitted from their surfaces arrives redshifted and weakened. These stars carry the imprint of collapsed matter, showing how spacetime responds when mass is crammed into smaller and smaller volumes. On even larger scales, individual stars merge into the sprawling structure of the galaxy. The Milky Way is not a flat disk floating in empty space. It is embedded in a vast, smooth gravitational well shaped largely by dark matter. Dark matter does not emit or absorb light, but its mass bends spacetime strongly enough to dictate the galaxy's structure. Stars orbit the galactic center at speeds too high to be explained by visible matter alone. The unseen dark matter creates spacetime curvature that holds the galaxy together, preventing it from flying apart. Without dark matter, galaxies could not exist in their current form. The motion of stars reveals this hidden curvature, exposing the structure of spacetime on scales far beyond human reach. The center of the Milky Way contains a supermassive black hole, Sagittarius A, whose immense curvature dominates the region around it, controlling the orbits of thousands of stars. The paths of these stars are measured with extraordinary precision, offering direct evidence of relativistic effects at galactic scales. Galaxies themselves interact with spacetime in remarkable ways. When two galaxies collide, their stars almost never physically hit each other because the space between stars is vast, but their spacetime wells merge, distort, and reshape each other. The geometry of the universe becomes malleable during these interactions. gas clouds compress and ignite star formation. Dark matter halos combine, creating deeper gravitational wells. Gravitational waves ripple outward from especially massive collisions. The cosmic dance that unfolds during galactic mergers is governed by space-time curvature, not random motion. Even when galaxies appear distorted or stretched in images, much of that visual effect comes from gravitational lensing, a direct sign of space-time bending light itself. As we zoom out farther, galaxies gather into clusters, massive structures containing hundreds or thousands of galaxies bound together by dark matter. These clusters create some of the strongest known gravitational wells in the universe. Light from background galaxies passing through these clusters experiences dramatic lensing, forming arcs, rings, and multiple images. These distortions map the curvature of spacetime within the cluster, revealing the distribution of mass. In these environments, spacetime is not smooth. It is lumpy, shaped by visible matter, dark matter, and hot gas. The geometry becomes complicated, producing unexpected pathways for light and unusual motions for galaxies. Yet the underlying framework remains consistent. Mass shapes curvature, curvature shapes motion. Clusters join into even larger structures, superclusters, and filaments. These colossal strands of galaxies and dark matter form the cosmic web, the largest structure in the universe. Space-time, on this scale, is shaped by density differences spread across hundreds of millions of light years. In dense regions, curvature deepens and matter flows inward. In empty voids, space-time expands more quickly. The cosmic web forms not because matter arranges itself arbitrarily, but because space-time curvature guides the flow of matter toward denser regions. Over billions of years, this flow sculpts the universe into an intricate network of filaments, walls, and voids. Each void represents a region where matter is sparse and space-time expands, with fewer obstacles. Each filament marks a dense region where curvature slows expansion and draws galaxies together. On the largest scales observable, the universe as a whole exhibits curvature influenced by its total mass energy content. Cosmological measurements indicate that the universe is nearly flat, though not perfectly so. This near flatness is itself a profound mystery. Inflation theories suggest that the early universe expanded so rapidly that any initial curvature was smoothed out. After inflation, the universe continued expanding, shaped by dark matter, dark energy, and radiation. The large-scale curvature determines the fate of the universe, whether it expands forever, slows down, or collapses. Current data indicate that dark energy drives accelerating expansion, stretching spacetime itself. This stretching influences the motion of galaxies, the propagation of light, and the shape of the cosmic microwave background radiation. Even the most ancient light in the universe carries imprints of spacetime curvature from when the universe was young. Across these scales, from Earth to the cosmic web, spacetime reveals consistent themes. Its curvature responds to mass and energy, whether they appear as planets, stars, clusters, or diffuse matter. Its geometry determines the pathways objects follow, whether they are satellites, photons, or galaxies. Its expansion stretches distances and redshifts ancient light. Its interaction with quantum fields produces fluctuations that influence structure formation. The behavior of spacetime does not change abruptly between scales. Instead, the effects accumulate, growing more dramatic as masses increase and distances expand. What changes is not the law, but the manifestation. On Earth, relativity hides behind familiar behavior. In the solar system, it appears in orbital motion. Around stars, it influences stellar evolution. In galaxies, it defines rotational dynamics. In clusters, it sculpts gravitational lenses. In the cosmic web, it organizes the universe into vast filaments. Across the entire cosmos, it guides expansion. The same equations govern all these phenomena. General relativity does not lose relevance. As scales broaden or narrow, it becomes increasingly essential. Understanding space-time across these scales is not merely an exercise in observation. It is a way of uncovering how the universe organizes itself, how structures arise from geometry, and how motion reflects deeper forces. When viewed through the lens of space-time, the universe reveals unity beneath diversity. Small-scale curvature around Earth, medium-scale curvature around stars and galaxies, and large-scale curvature across cosmic voids all express the same underlying principle. Geometry rules the cosmos. Across the universe, matter does not scatter randomly. It gathers into patterns so immense that the human mind struggles to comprehend them. These patterns are not created by chance. They are written by space-time itself. Once you zoom out far beyond galaxies and their clusters, the true architecture of the cosmos emerges, an intricate network of filaments, threads, knots and voids stretching across billions of light years. This is the large-scale structure of the universe, the cosmic web, and it is one of the clearest demonstrations that space-time is not an empty backdrop, but an active sculptor of cosmic evolution. Gravity, dark matter, dark energy, cosmic expansion, and quantum fluctuations all contribute to its formation. But the underlying framework that organizes everything is space-time curvature. To understand the cosmic web, you must begin at the earliest known moment when the universe became transparent. Around 380,000 years after the Big Bang, electrons and protons combined to form neutral atoms. Light was finally free to travel, and the cosmic microwave background radiation began its journey. This radiation carries tiny temperature variations, fluctuations only 1 part in 100,000, that represent small differences in density. These slight variations were the seeds of future structure. Without them, matter would be uniformly distributed, and the cosmos would contain no galaxies, no stars, no planets, no observers. These small ripples were amplified by the interplay between gravity and cosmic expansion. Regions that were slightly denser pulled in more matter, deepening their gravitational wells. Regions that were slightly less dense expanded more rapidly, forming the beginnings of cosmic voids. The geometry of space-time responded to these density differences, bending more deeply around overdense areas and flattening or stretching in underdense areas. As the universe continued to expand, these seed regions grew into the foundations of large-scale structure. Dark matter, invisible but gravitationally dominant, fell into these wells first. Because dark matter does not interact with light or collide with itself, it moved freely through space, clumping rapidly under its own gravity. Normal matter, interacting with radiation, followed more slowly. Space-time curved around the growing clumps, shaping the flow of matter like a landscape guiding rivers. Over hundreds of millions of years, the universe organized itself into a network of interconnected structures, filaments where matter concentrated, nodes where filaments crossed, sheets that stretched between them, and vast voids where matter was scarce. The curvature created by these distributions guided further motion, drawing matter along the paths defined by the geometry. This process did not occur in isolation. The expansion of the universe played a critical role. While gravity pulled matter together into overdense regions, dark energy drove the overall expansion, stretching the web. The tug-of-war between these forces shaped the cosmic landscape. In dense regions, gravity overcame expansion and formed bound structures like galaxies and clusters. In empty regions, expansion dominated, creating voids that grew larger as matter flowed toward the filaments. Space-time was not static during this process. It was continually reshaped by the shifting balance of forces. The cosmic web is not a frozen structure, but a dynamic pattern that evolves as the universe expands. The most prominent features of the cosmic web are filaments, long rope-like structures containing massive amounts of dark matter and gas. These filaments are the highways of the universe, carrying matter toward galaxy clusters. Galaxies form preferentially within these channels, aligning themselves with filamentary directions. Spacetime curvature along these filaments creates a gravitational pull that funnels gas and dark matter inward. Observations show that galaxies within filaments rotate differently, form stars more rapidly, and cluster along the filament's spine. These behaviors reveal the influence of spacetime geometry on galactic evolution. Filaments stretch across hundreds of millions of light years, yet they maintain a coherent structure shaped by gravity and expansion working together. Where filaments intersect, galaxy clusters form. These clusters are the largest gravitationally bound objects in the universe, containing thousands of galaxies, hot X-ray emitting gas, and enormous reservoirs of dark matter. The curvature around these clusters is among the strongest observed outside of black holes. Light passing near a cluster is deflected dramatically, an effect that produces arcs, rings, and distorted shapes in background galaxies. These lensing patterns allow astronomers to map the distribution of dark matter with remarkable accuracy. The cluster's gravitational potential wells are so deep that they slow the flow of time more noticeably than typical galactic regions. In these dense intersections, spacetime bends steeply, guiding the motion of galaxies like stones caught in a whirlpool. Beyond the clusters lie vast cosmic voids, enormous regions where matter is sparse, and spacetime expands more rapidly than in denser regions. Voids are not empty. They contain a diffuse population of galaxies and dark matter, but their density is far lower than average. The expansion of space within voids is relatively unimpeded by gravity, causing them to balloon outward. These voids push matter toward filaments and walls, helping define the boundaries of the cosmic web. The geometry inside voids is flatter than in dense regions, and their rapid expansion subtly affects the redshift of galaxies observed within them. Studying voids allows scientists to probe dark energy, cosmic expansion, and the uniformity of spacetime. In a sense, voids are laboratories where the universe reveals how spacetime behaves when gravitational curvature is minimal. The cosmic web emerges through gravitational instability, the natural amplification of density fluctuations in an expanding universe. But the details of its shape depend on the properties of dark matter. Because dark matter interacts only through gravity, it creates smooth, large structures rather than clumpy, small ones. If dark matter behaved differently, if it collided with itself or interacted strongly with light, the cosmic web would look radically different. Its large-scale structure therefore provides clues to the nature of dark matter. Reconciling dark matter with spacetime geometry remains one of the central challenges in cosmology, and the cosmic web offers a map for solving it. Spacetime also influences how galaxies move within these structures. Galaxies do not simply drift randomly through the universe. They're guided along the contours of gravitational potential determined by the cosmic web. Their velocities reveal the shape of spacetime around them. Regions of high density pull galaxies inward, while voids repel them. The large-scale flow patterns, known as cosmic flows, map the curvature of spacetime across enormous distances. Observations of these flows help identify attractors, regions where mass concentrations pull galaxies from across vast expanses. The Shapley supercluster and the Great Attractor are examples of massive structures whose influence extends across hundreds of millions of light years. These regions curve spacetime strongly enough to alter the motion of entire galactic populations. Gravitational lensing provides another window into the geometry of the cosmic web. When light from distant galaxies passes through curved regions of spacetime, it distorts in predictable ways. Weak lensing, the subtle stretching and shearing of galaxy shapes, creates patterns across the sky that correspond to the underlying distribution of matter. By studying these distortions, scientists create detailed maps of the cosmic web's mass distribution. These maps reveal that dark matter forms the skeleton of the universe. Normal matter gathers around this skeleton, forming galaxies and gas clouds. The lensing patterns not only confirm the existence of dark matter, but also constrain its properties. They show how space-time responds to mass on the largest scales imaginable. At even larger scales, the curvature of space-time determines the overall geometry of the universe. Measurements of the cosmic microwave background reveal how light traversed the universe shortly after its formation. Small temperature variations in this ancient light encode the curvature of space-time across scales larger than galaxy clusters. These measurements show that the universe is remarkably flat, meaning that the geometry of large-scale space-time is close to Euclidean. But flat does not mean empty or static. It means that the total density of matter and energy balances the curvature. This near flatness is itself a clue to the universe's early evolution, suggesting that inflation, an era of exponential expansion, smoothed space-time to extraordinary precision. Despite this large-scale flatness, the universe is anything but uniform. The interplay of dark matter, dark energy, and cosmic expansion creates regions of different curvature. Observing how these regions evolve helps cosmologists refine their models of the universe's history. The behavior of the cosmic web reflects the influence of dark energy, which accelerates expansion. This acceleration stretches the web, slowing the growth of structure. If dark energy did not exist, the cosmic web would look denser, with more clusters and thicker filaments. By comparing observed structures with simulations, scientists determine how space-time evolves under the influence of dark energy. This makes the cosmic web not only a map of matter, but also a tool for measuring the universe's expansion history. The evolution of the cosmic web reveals that space-time is dynamic. Filaments grow as matter flows along them. Clusters merge as their gravitational wells deepen. Voids expand as matter drains toward filaments. These changes occur over billions of years, but they follow deterministic rules set by Einstein's equations and the universe's energy content. In this way, the large-scale structure acts like a fossil record of space-time. It shows how tiny fluctuations in the early universe developed into the structures we observe today. It reveals how matter interacts with geometry and how geometry responds. It demonstrates that space-time is not fixed but evolving, influenced by every particle of mass and energy. The cosmic web's scale and complexity highlight the deep unity of the universe. The same laws that govern falling apples, planetary orbits, and light bending near stars also govern the arrangement of galaxies across billions of light years. The structure of the cosmos reflects the structure of space-time. By studying the web, scientists glimpse the universe's underlying geometry, the forces shaping it, and the mysterious components, dark matter and dark energy, that dominate its behavior. The science of space-time is still in its early chapters. Everything humanity has discovered so far, relativity, black holes, expanding space, gravitational waves, the cosmic web, represents only the surface of a far deeper reality waiting to be uncovered. The next century of physics will not simply refine what we know, it will likely transform our understanding of the universe's structure in ways that even Einstein could not have imagined. The tools being built today will allow scientists to measure space-time with unprecedented precision, observe gravitational phenomena across unimaginable distances, probe the moment of cosmic birth, and test whether space-time itself is fundamental or emergent. The future of space-time science is not only about answering old questions, it is about asking questions no one previously had the capacity to ask. Humanity's ability to observe space-time began with telescopes that captured light. But the next era will rely on instruments that capture geometry directly. Gravitational wave observatories such as LIGO and Virgo demonstrated that spacetime can vibrate like a cosmic drum. Their detections revealed black hole collisions, neutron-star mergers, and signals from objects once hidden from view. But these detectors sense only the loudest, most violent events. They are sensitive to specific frequencies where massive objects crash into each other. The future holds far more ambitious plans. Upgrades to LIGO will increase sensitivity, allowing detection of smaller black holes, longer in spirals, and subtle ripples produced by cosmic events billions of years ago. Virgo, Kagra, and new detectors in India will create a global network capable of pinpointing gravitational wave sources with greater accuracy. Even more transformative will be LISA, a space-based gravitational wave observatory consisting of 3 spacecraft separated by millions of kilometers. Instead of listening for short bursts from stellar collisions, LISA will detect deep, slow, rumbling waves produced by massive black holes at the centers of galaxies. It will listen to the gentle murmurs of white dwarf binaries orbiting each other for millions of years. It will sense how spacetime stretches across the Milky Way. With LISA, scientists will gain access to a gravitational soundtrack of the universe that Earth-based detectors cannot hear. These observations will test general relativity in regimes far beyond current experiments. If spacetime behaves differently at large scales, or if gravitational waves disperse or change polarization in ways relativity forbids, LISA will reveal those deviations. The data may confirm Einstein's theory once again, or expose cracks that lead toward a new theory of gravity. The Event Horizon Telescope, which captured the first image of a black hole's shadow, is only the beginning of a new era of spacetime imaging. Future upgrades will add more telescopes around the world, improving resolution and allowing scientists to watch black holes evolve in real time. Imaging will extend beyond still pictures to movies, revealing how matter swirls, jets erupt, magnetic fields twist, and spacetime near the event horizon fluctuates. These observations will test whether black hole shadows match predictions precisely or show subtle discrepancies indicating quantum effects or deviations from general relativity. If the geometry near a black hole differs even slightly from Einstein's equations, future observations will detect those deviations. Black holes are no longer theoretical curiosities. They are laboratories where spacetime can be studied directly. Another frontier involves exploring spacetime at cosmic scales. Dark energy remains one of the greatest mysteries in science, and its effects become more pronounced as the universe expands. New missions such as the Euclid satellite, the Nancy Grace Roman Space Telescope, and the Vera C. Rubin Observatory will map billions of galaxies, measuring how spacetime curvature evolves across cosmic history. These surveys will reveal how the expansion rate changes over time, whether dark energy is constant or dynamic, whether spacetime geometry remains smooth or fluctuates, and whether gravity behaves differently across vast scales. If the universe's acceleration deviates from predictions, it would suggest the existence of new physical laws or additional fields influencing spacetime. Simultaneously, the study of dark matter will probe spacetime from a different direction. While dark matter has never been observed directly, its gravitational influence on galaxies and clusters shapes spacetime on large scales. Upcoming experiments aim to detect dark matter interactions, map its distribution with higher resolution, and search for new particles or exotic objects that might explain its behavior. These investigations will reveal whether dark matter is composed of particles, fields, or something more exotic, like primordial black holes. Each possibility offers clues about how spacetime interacts with unseen components of the cosmos. Advances in quantum technology will allow scientists to probe spacetime on small scales. Quantum sensors, devices that use entangled particles or precision atomic clocks, will detect minuscule variations in gravitational potential with unprecedented accuracy. Clocks so precise they lose less than a second over the age of the universe, will map spacetime curvature across rooms, buildings, and laboratories. These instruments will test the smoothness of spacetime, measure gravitational redshift in tiny increments, and search for fluctuations predicted by quantum gravity theories. Quantum interferometers could one day detect microscopic ripples in spacetime or reveal deviations from classical geometry. Such experiments bring humanity closer to probing the Planck scale, where quantum and gravitational effects intertwine. The future of cosmological simulations looks equally promising. Modern supercomputers already simulate billions of particles forming galaxies, clusters, and cosmic webs. But future simulations will incorporate relativistic physics more fully, modeling how spacetime evolves dynamically rather than treating it as a static background. Algorithms will simulate gravitational waves, quantum fields, dark energy dynamics, and black hole mergers as part of a unified cosmic environment. These simulations will not only reproduce the universe we see, but allow scientists to test alternative laws of physics and compare them to observational data. If a modified theory of gravity predicts a different cosmic web or distribution of galaxies, simulations will reveal those differences long before telescopes do. In laboratories, physicists will continue building analog models of spacetime. Experiments with superfluids, Bose-Einstein condensates, and optical waveguides can mimic certain aspects of curved spacetime, such as horizons, particle creation, or wave propagation. While these models are not literal replacements for gravitational experiments, they provide platforms for testing mathematical predictions and exploring phenomena like Hawking radiation or emergent geometry. These experiments suggest a compelling possibility. Spacetime may arise from underlying quantum processes in the same way that fluid dynamics arises from molecular interactions. If spacetime is emergent, the search for quantum gravity becomes not a search for smaller atoms of space, but a search for the fundamental rules that produce geometry as a large-scale effect. The future also holds the possibility of discovering entirely new phenomena. If nature includes extra dimensions, gravitational waves could leak into them or return signals with unusual signatures. If gravity weakens or strengthens over cosmic distances, cluster formations and the cosmic web would reveal those changes. If black holes contain quantum remnants or exotic structures instead of classical singularities, future observations could detect echoes in gravitational wave signals or deviations in shadow shapes. If spacetime foam, the hypothesized fluctuation at the Planck scale, affects light from distant quasars, astronomers may detect tiny distortions in their arrival times or spectra. Each of these possibilities would reshape modern physics. The search for quantum gravity, the final unification of gravity and quantum mechanics, remains the central goal driving much of this research. Whether the correct description involves strings vibrating in higher dimensions, loops of quantized geometry, holographic dualities, or entirely new frameworks remain unknown. But the future will bring tools capable of testing these theories. Gravitational wave echoes, microscopic time dilation fluctuations, deviations in the cosmic expansion rate, or unusual black hole behaviors may provide the first glimpses of a quantum spacetime. Theories that once seemed purely mathematical could gain empirical support. Others may be discarded. The path to quantum gravity will depend not on philosophical reasoning, but on observation. Humanity's exploration of spacetime will also deepen as technology expands beyond Earth. Future space missions may place telescopes on the Moon, providing a stable foundation for far infrared or gravitational wave detectors. Arrays of satellites could form interferometers spanning hundreds of thousands of kilometers, capturing signals with unprecedented clarity. Deep space probes equipped with precision clocks could test relativity in regions of the solar system where curvature differs from Earth's environment. As exploration extends toward Jupiter Saturn, and beyond, spacecraft will measure how space-time geometry changes across the solar system in real time. Even interstellar travel, if it ever becomes feasible, would unfold within the framework of space-time science. High-velocity spacecraft would experience time dilation, requiring mission planners to incorporate relativistic effects into navigation and communication. If future propulsion systems exploit space-time geometry, perhaps through warp fields or exotic energy configurations, they would rely on principles rooted in the very fabric of the universe. While such technologies remain speculative and far beyond current capabilities, the boundaries of possibility will expand as our understanding of space-time deepens. Ultimately, the greatest transformation in the future of space-time science will not be technological, but conceptual. The more humanity learns about space-time, the more it becomes clear that the universe is not a static container, but a dynamic, evolving, interconnected structure. The curvature that defines motion, the expansion that stretches galaxies apart, the quantum fields that ripple beneath reality, the gravitational waves that vibrate across billions of light years. All of these phenomena reveal a universe far stranger and more profound than the one people once imagined. The next breakthroughs will not simply add detail, they will reshape foundational ideas about what space and time are, how they emerge, and what lies beyond them. The future of space-time science will bring new instruments, new data, new theories, and new challenges. It will require humility in the face of the unknown and imagination to interpret signals that speak the language of the cosmos. Einstein once unified space and time into a single fabric. The next revolution may show that this fabric is only one layer of a deeper reality. Humanity stands at the edge of that discovery, listening to the universe whisper through space-time, waiting for new clues woven into the geometry of existence. When people first discover that space and time fuse into a single geometric structure, it often feels like a mathematical abstraction, clever, elegant, but distant from personal experience. Yet the deeper one explores space-time, the more it becomes clear that it touches the most intimate and profound questions humans ask. What is the nature of reality? What does it mean for something to exist? Why does time move forward? Is the universe predetermined? What role does consciousness play in interpreting a world where past and future coexist in geometry? Scientific theories rarely brush so close to philosophy, but space-time forces the conversation. It demands that we confront the limits of intuition and redefine concepts that once felt obvious. One of the most challenging ideas that emerges from space-time is that the universe does not evolve, frame by frame, the way human consciousness perceives it. Instead, all events, past, present, and future, appear as fixed points in a four-dimensional structure. This view, sometimes called the block universe, is not a metaphysical claim, but a direct consequence of relativity's geometry. If simultaneity is relative, if observers in different states of motion slice space-time into different nows, then no single universal present exists. What you experience as the moment is simply the cross-section of your world line through space-time. Someone moving differently will cut a different slice. This does not mean the future is predetermined in a mystical sense. It means that time is a dimension, not a flowing substance. The flow is something the brain creates, not something the universe imposes. Even though this interpretation follows naturally from relativity, many physicists treat it as a philosophical perspective rather than a literal description. The scientific consensus accepts the relativity of simultaneity and the geometric nature of space-time. But whether time truly exists all at once remains a debated philosophical interpretation. What is clear is that physics does not distinguish between past and future in its fundamental equations. The laws work equally well forward and backward in time. The arrow people feel, the movement toward the future, is a product of thermodynamics, entropy increases, and cognitive processes shaped by evolution. These concepts explain why time appears to flow, but they do not require time itself to flow in a physical sense. Another philosophical question emerges from the relativity of time. Because observers moving differently age at different rates, there is no single objective measure of how much time has passed between two events. Proper time, the time experienced along a world line, is personal, not universal. Two individuals may meet, separate, and reunite with vastly different amounts of experienced time between the meetings. This does not violate physics. It is dictated by spacetime geometry, but it challenges deeper assumptions about identity, aging, memory, and existence. If time is experienced differently, depending on motion and gravity, then human lifetimes are not absolute durations, but relationships between world lines. A lifetime is a path, not a number. This leads naturally to discussions about determinism and free will. If space-time is a fixed geometric structure, does that mean the future is as unchangeable as the past? In classical general relativity, space-time does not grow, it simply is. But this does not necessarily eliminate free will. The idea that the universe is fixed is a consequence of the mathematical description, not a proven metaphysical truth. Moreover, quantum mechanics introduces uncertainty, probability, and indeterminacy, though whether these represent true randomness or deeper hidden variables remains debated. Some interpretations of quantum theory, such as the Copenhagen interpretation or objective collapse models, suggest that events do not become definite until measured. Others, like the many worlds interpretation, propose that all outcomes occur in separate branches of spacetime. These interpretations remain speculative and are not considered proven science. What physics can say with confidence is that spacetime geometry constrains what is possible, but it does not dictate how choices arise within those possibilities. At the same time, spacetime reveals that causality is more robust than intuition suggests. Even though simultaneity is relative, cause and effect remain preserved because of light cones. No event can influence another outside its future light cone, and no event can be influenced by something outside its past light cone. This structure is not philosophical, it is physical, built into the geometry of spacetime, and validated by every experiment. It ensures that information cannot travel faster than light, preserving consistency in all frames of reference. Causality becomes a geometric relationship, not a temporal one. Where you are in spacetime determines what can influence you and what you can influence, independent of how your consciousness interprets it. The nature of existence itself becomes more complicated in this framework. What does it mean for something to exist now, if the present is not fundamental? In spacetime, existence is tied to world lines, interactions, and events. Objects exist because they trace continuous paths through spacetime. Events exist because they occur at specific coordinates in that geometry. Existence becomes distributed, not localized in time. Philosophically, this challenges everyday assumptions but aligns cleanly with physics. When a star explodes in a distant galaxy, that explosion exists in spacetime even before its light reaches Earth. The event is not created when observed, it is only discovered. This does not imply that observation changes reality, it simply reflects the structure of spacetime. Spacetime also challenges ideas about space as something passive. People often think of space as a container holding matter. But in relativity, space does not exist without matter and energy. Remove all matter, radiation, and fields, and spacetime geometry still depends on vacuum energy and quantum fluctuations. If those were removed, a hypothetical scenario, spacetime itself might cease to behave as space. This raises philosophical questions about whether space is a physical thing, a mathematical construct, or an emergent phenomenon. Some speculative theories, not accepted as proven science, propose that space-time emerges from quantum entanglement patterns or information networks. These ideas come from attempts to unify quantum mechanics with general relativity. If future experiments support such frameworks, the very concept of space-time might be reframed as a higher-level construct built from something deeper. For now, space-time remains the best description of the universe's structure, even if its ultimate origin is unresolved. Another deep question arises when considering the role of observers. In relativity, each observer constructs their own coordinate system, slicing space-time differently and measuring time differently. But the underlying geometry remains consistent across all observers. Physics cares about the invariants, the quantities that remain unchanged regardless of perspective. Proper time, curvature, geodesics, and causal structure belong to this invariant category. This suggests a philosophical lesson. Objective reality exists, but human perception of it is always filtered through motion, position, and sensory limitations. The universe's true structure is geometric, not experiential. Consciousness raises additional questions. Humans experience time subjectively as a sequence of moments. But if physics treats time as a dimension rather than a flowing river, what does this mean for the mind? Neuroscientists explain the perception of time as the result of memory formation, sensory integration, and cognitive prediction. Nothing in physics suggests that consciousness plays a role in shaping space-time or determining outcomes. Even quantum mechanics, often misinterpreted in popular culture, does not require consciousness to collapse wave functions in mainstream scientific interpretations. The relationship between human experience and space-time appears one-directional. Space-time shapes the environment in which brains evolve, and the brain creates subjective experience. The universe does not depend on observers to exist, yet the fact that consciousness exists within space-time leads to a philosophical reflection that is neither scientific nor supernatural. It is simply human. The geometry that shapes galaxies, stars, and the cosmic web also shapes the world lines of conscious beings. Every thought, memory, decision, and emotion occurs along a path in space-time. Even personal identity is encoded as a series of events. In this sense, space-time becomes not just a physical structure, but a narrative medium. A human life is a curve drawn through the universe, influenced by curvature, motion, and choices. Physics does not assign meaning to this curve, but people do. Space-time provides the canvas. Consciousness paints the story. Another philosophical implication arises from the observation that space-time is dynamic. It expands, stretches, curves, vibrates, and evolves. This means that the universe is not a static stage, but an active, living structure. When gravitational waves ripple, space-time itself becomes part of the phenomenon. When dark energy drives expansion, space-time stretches. When mass moves, space-time responds. This interactive quality blurs the boundary between object and environment. The universe becomes a self-organizing system where geometry and matter co-create structure. Whether this suggests deeper principles, such as emergent behavior or self-organizing laws, remains an open question. It is not established science, but it is a philosophical perspective inspired by physics. Even the concept of locality becomes philosophical. In everyday life, locality means that physical interactions happen only between nearby things. But in quantum mechanics, entangled particles share correlations across any distance. While these correlations do not violate relativity or transmit information faster than light, they challenge classical intuitions about separateness. Some speculative theories propose that space-time itself may emerge from networks of entanglement. If true, then distance is not fundamental, but derived. This idea remains unproven and must be labeled as speculative, not scientific consensus. But it illustrates how understanding spacetime pushes the boundaries of thought. The ultimate philosophical challenge of spacetime, however, may be the question of origins. What came before the Big Bang? Did spacetime emerge? Did time begin? General relativity predicts a singularity at the Big Bang, a point where curvature becomes infinite and the equations break down. But physicists agree that this singularity is a signal of incomplete knowledge, not a literal point in reality. The beginning of spacetime remains an open question. Quantum gravity theories suggest various possibilities: a bounce, a transition from a previous phase, or an emergent structure that renders before meaningless. None of these ideas have experimental confirmation. All remain speculative. What is certain is that spacetime, as described by general relativity, cannot fully answer questions about its own origin. In the end, the philosophical significance of spacetime lies not in resolving metaphysical puzzles, but in revealing how deeply intertwined geometry and reality are. Space and time are not absolute containers. They are relational, dynamic, and shaped by energy. The universe is not a collection of objects, but a network of events connected by geometry. Time is not a river flowing forward, but a dimension structured by causality and entropy. Consciousness does not sit outside this structure, but moves within it. Reality becomes a tapestry of interactions, world lines, and curvature. Understanding spacetime does not diminish the human experience. It enriches it. Knowing that every moment lived and every choice made traces a unique path through the cosmos gives new meaning to existence. Knowing that the atoms in your body respond to curvature, that your lifetime is measured as proper time along a world line, and that your experiences unfold within a structure older and larger than imagination, creates a sense of connection to the universe that transcends scale. The cosmos is not distant, it is the geometry that holds you. The journey through space-time ends where it began, with a simple but profound realization. The universe is not what intuition suggests. What feels solid is mostly emptiness. What seems steady is constantly changing. What we experience as time is not an external river pulling us forward, but the unfolding of our own motion through the fabric of reality. Space and time are fused into a single structure, shaped by mass and energy, responsive to motion and curvature, and stretching effortlessly across billions of light years. After exploring its depths from the smallest scales of quantum uncertainty to the colossal patterns of the cosmic web, spacetime becomes more than a theoretical construct. It becomes the language of the universe. If there is one message that emerges from everything science has revealed, it is that spacetime is the framework within which all physical processes take place. It determines how planets orbit, how stars evolve, how galaxies form, and how the universe expands. It dictates how clocks tick, how light travels, and how gravity works. It explains why time passes differently for different observers, and why nothing can outrun a beam of light. It reveals how black holes distort reality, how gravitational waves ripple across the cosmos, and how the universe organizes itself into vast filaments of matter, stretching across unimaginable distances. Whether studying the life of a star or the behavior of a single photon, spacetime is always the stage and often the main performer. Throughout history, humanity has struggled to understand the fundamental nature of existence. The concept of spacetime does not answer every philosophical question, but it dissolves many illusions that once seemed unquestionable. Space is not empty. Time is not absolute. Gravity is not a pull but a curve. Motion is not universal but relative. Even the idea of a shared now crumbles under examination, replaced by a geometry in which different observers construct their own slices of time. These revelations do not diminish human experience. they deepen it. They show how intimately connected humans are to the universe they inhabit, how each breath taken and each step made occurs within the structure shaped by cosmic forces billions of years old. Some aspects of space-time remain solidly within scientific consensus. The relativity of simultaneity, gravitational time dilation, the curvature produced by mass, the equivalence principle, black hole horizons, gravitational lensing, and the expansion of the universe have been confirmed through observation and experiment. These principles are not speculation. They form the foundation of modern physics. They explain everything from the precession of Mercury's orbit to the timing corrections needed for GPS. They allow astronomers to map dark matter, interpret distant galaxies, and measure gravitational waves. They ground our understanding of cosmology and guide the design of technology. These truths are as real and verified as any scientific discovery ever made. Other ideas explored along the way fall into speculation or interpretation. Whether the block universe is literally real, whether space-time is emergent from quantum entanglement, whether black hole singularities can be resolved by quantum gravity, whether additional dimensions exist, or whether time began at the Big Bang, these questions remain open. They offer direction for future research, but they lack definitive evidence. Distinguishing what is known from what is hypothesized keeps the scientific journey honest. Science thrives on the boundary between understanding and mystery. Space-time sits on that boundary, simultaneously revealing and concealing the deeper layers of reality. The future of space-time research promises new discoveries that may transform our understanding once again. Next-generation gravitational wave observatories will listen to the universe with unprecedented sensitivity. New telescopes will watch black holes in real time. Quantum technologies will measure tiny fluctuations in gravitational potential. Cosmological surveys will map billions of galaxies to uncover how space-time evolves. Experiments may one day detect quantum gravity signatures or reveal that space-time itself is not fundamental but emergent. These possibilities are not guaranteed, but they reflect the direction modern science is heading. Each discovery will refine or challenge existing theories, bringing humanity closer to the ultimate goal of uniting general relativity and quantum mechanics. Yet despite all this progress, the mystery of space-time remains profound. Even the simplest questions, what is space? What is time? Why does the universe have the structure it does? Still have no complete answers. General relativity explains how space-time behaves, but not why it exists. Quantum mechanics reveals probabilities and uncertainty, but not the underlying mechanism. Cosmology maps the universe's expansion, but not its origin. These gaps are not failures, they are invitations. The more humanity learns, the more beautiful the unknown becomes. In reflecting on everything space-time contains, galaxies swirling through dark matter halos, stars orbiting black holes, gravitational waves trembling across the cosmos, photons escaping dying suns, matter collapsing into neutron stars, clusters gathering into superclusters, it becomes clear that the universe is not chaotic. It is structured. It has architecture. And that architecture comes from geometry. Even consciousness, which sits at the intersection of biology and physics, unfolds within the framework of space-time. The memories that define a person, the choices that shape a life, and the experiences that give meaning to existence all occur along a world line that weaves through the cosmic fabric. Humanity does not stand outside the universe observing it. Humanity is embedded within it. There is a quiet humility in realizing that the same geometry that governs planets also governs personal experiences. The space-time curvature that holds galaxies together also determines how fast a heart ages. The expansion of the universe creates the background against which civilizations rise and fall. The gravitational waves that ripple from distant collisions pass silently through your body. Every person is a participant in this cosmic dance, shaped by forces they cannot feel, yet rely on entirely. Spacetime also encourages a broader perspective. When looking up at the night sky, the stars are not scattered randomly. They trace the structure of the cosmic web. Their light has traveled through the curvature created by dark matter, past galaxies and clusters, through expanding space. Seeing them is seeing across time, as well as distance. A star shining today may have died long ago. A galaxy visible now may never have existed in the form perceived. Light is a messenger of space-time, carrying stories written billions of years before humanity existed. Understanding this does not make the sky feel colder. It makes it feel alive. The journey through space-time also changes how humans view themselves. On one hand, it reveals that Earth is a tiny speck in a universe of unimaginable scale. Human lifetimes are brief, and personal concerns vanish when compared to cosmic timescales. But on the other hand, the very fact that humans can understand space-time is extraordinary. The universe has produced beings capable of reflecting on the structure of reality, capable of questioning their own existence, capable of deciphering light emitted before Earth formed. Consciousness may be a local phenomenon, but the curiosity that drives it is cosmic. In learning about space-time, humanity reconnects with its origins. As the exploration of space-time continues, future generations will look back on this moment as a turning point. The era when humans first learned to measure time dilation in laboratories, detect gravitational waves from distant black holes, map the cosmic web, and capture images of horizons shaped by pure geometry. They will see this as the beginning, not the end, of humanity's understanding. What lies ahead will be deeper, stranger, and more beautiful. Whether the universe expands forever or ends in a collapse, whether space-time is continuous or discrete, whether reality contains hidden dimensions or emerges from quantum information, each answer will reveal new questions. The pursuit of knowledge is endless because space-time is endless. What remains certain is this: the universe is intelligible. It follows laws that can be discovered, tested, and refined. Humans may not yet know the final theory that unites gravity with quantum mechanics, but they know enough to see the path forward. Space-time is both the roadmap and the terrain. It is the container and the content. It is the background and the actor. It is the silent structure that gives shape to everything. In the end, understanding space-time is not about equations, metrics, or coordinate systems. It is about understanding what it means to exist in a universe where geometry is destiny. It is about recognizing that every life, every moment, every movement is part of a much larger story, a story written in the curvature of space-time. And even though the universe is vast and ancient, it is not indifferent. It gave rise to consciousness capable of witnessing it. The cosmos is not simply something to observe, it is something to belong to. That is the ultimate message of space-time. You are part of the universe, and the universe is part of you. Your path through space-time is unique, irreplaceable, and woven into the cosmic fabric forever. The universe moves, curves, expands, and evolves, and you move with it, carving your own world line in the grand geometry of existence.